Hello and welcome to Sleepy Science. What if reality does not always decide which event happened first, where a particle truly was, or whether the same fact exists for every observer? What if energy can be present but unusable? Entanglement can hide inside states that appear almost ordinary, and a quantum machine can complete a task without following any definite sequence of steps. In this journey, you will explore experiments and theories that challenge the familiar boundaries between objects. Information, cause, time, and observation, not through science fiction, but through some of the strangest ideas modern quantum physics seriously allows. Before we begin, don't forget to like the video and subscribe. And as these hidden rules slowly unfold, you may begin to wonder whether reality is made of definite things at all, or of relationships that become meaningful only when the universe is forced to answer a question. Quantum physics may allow facts that are true for one observer but not another. Imagine watching a scientist enter a perfectly isolated laboratory, measure a quantum particle, and write the result in a notebook, while you remain outside with no access to anything that has happened within. For the scientist inside, the experiment appears completely ordinary. The detector flashes, one definite result is recorded, and a new fact enters their world. The particle was found in one condition rather than another, yet quantum theory allows the observer outside to describe the sealed laboratory very differently. If the room has truly remained isolated from its surroundings, the external observer may treat the particle, the detector, the notebook, and even the scientist as parts of one larger quantum system that has not settled into a single outcome. From the inside, a definite event has occurred. From the outside, the laboratory may still be represented as a combination of several possible outcomes. This tension is explored through a thought experiment known as Wagner's friend. It does not merely ask whether two people can hold different opinions. Their disagreement is deeper than interpretation or incomplete information. Each observer applies the same quantum rules from a different physical position, and those rules seem to permit descriptions that cannot easily be placed inside one shared account of what happened. The scientist says, "I saw a definite result." The observer outside says, "The entire room may still be in a quantum superposition." Both statements can follow logically from the information available to the person making them. This does not mean that anyone can invent whatever reality they prefer, nor does it prove that everyday facts become true only when someone believes them. The problem appears under extremely controlled conditions involving isolation, measurement, and the assumption that quantum theory applies universally, even to observers and their equipment. Researchers have performed small-scale experiments inspired by this puzzle, often replacing human observers with photons, detectors, or quantum memories. These experiments do not place conscious people into visible superpositions, but they test the deeper assumptions behind the scenario. Some results show that it may be impossible to preserve all of our familiar beliefs at once. We may have to reconsider the idea that every measurement produces one observer-independent fact, or question whether quantum theory can be applied without limitation to every level of an experiment. Other possibilities involve rejecting certain assumptions about locality, measurement choices, or how different observers combine their knowledge. The important lesson is not that science has discovered several magical realities floating beside one another. It is that quantum theory makes the phrase, "what actually happened," more difficult to define than it appears. In ordinary life, facts seem to belong to the world itself. A glass breaks, a door closes, a light turns on, and everyone can eventually agree that the event occurred. But at the quantum level, a fact may first exist as a relationship between a system and the observer who interacted with it. Another observer, standing farther away and treating both as one undisturbed system, may not yet be able to include that fact in the same way. Reality begins to resemble a network of encounters rather than a single book in which every result is written for everyone at once. And perhaps the quietest mystery is not that observers may disagree, but that the universe still allows them to meet, compare records, and build a common world afterward. Somewhere between the private moment of measurement and the shared language of science, possibilities become memories, records become facts, and separate viewpoints settle into something stable enough for you to call reality. Two events can happen without reality, choosing which one came first. Suppose a message must pass through two machines before reaching its destination. One machine changes its shape, while the other changes its direction, and in the familiar world, the order matters. The first machine acts, then the second, producing a result shaped by that sequence. You could reverse the machines and obtain a different outcome, but there would always be a clear answer to the question of which operation happened first. Quantum physics allows a stranger arrangement. In a process known as the quantum switch, a quantum system can control the order in which two operations occur, placing the sequence itself into a coherent combination. Along one part of the process, operation A occurs before operation B. Along another, operation B occurs before operation A. Crucially, the experiment is not merely choosing one order at random and hiding the choice from you. A random mixture would mean that one definite sequence happened each time, even if you did not know which one. In a quantum switch, the two possible orders can remain linked as quantum alternatives and later interfere, allowing the final result to contain information from both arrangements. The uncertainty is therefore not simply inside your mind. Under the quantum description, the process may possess no single fixed order before the relevant measurement is completed. This sounds like an effect occurring before its cause, but that interpretation goes too far. The quantum switch does not allow a person to send a warning into yesterday, erase an event that has already happened, or create the familiar paradoxes of time travel. Each individual operation still takes place through an ordinary physical interaction, and no usable message is sent backward through time. What becomes indefinite is the global relationship between the operations. Reality does not always provide one classical timeline that places every step into a universal first and second sequence. Researchers have demonstrated quantum switch-like processes using particles of light whose paths or other quantum properties control the order of operations. When the alternatives remain coherent, the system can perform certain information processing and communication tasks more efficiently than comparable procedures restricted to a fixed order. The advantage does not come from the particle moving infinitely fast or doing unlimited calculations. It comes from allowing the structure of the procedure itself to become a quantum resource. Instead of placing events on a rigid track, the experiment lets more than one ordering contribute to the same final outcome. This idea forces a subtle change in how you think about causality. You normally imagine cause and effect as the deepest framework beneath all events, like rails that the universe must follow. Yet the quantum switch suggests that a fixed causal order may sometimes be a property of the large stable world, rather than an unavoidable feature of every microscopic process. At ordinary scales, interactions with the environment destroy delicate quantum relationships so rapidly that events settle into reliable sequences. Cups fall before they shatter. Questions are asked before answers are heard. Your memories arrange themselves along a direction that feels permanent. But beneath that familiar order, nature may permit processes whose steps cannot be placed into one definite arrangement without losing part of what the experiment reveals. Two events can remain connected without reality declaring one universally first. And as the system finally interacts with the detector and leaves a stable record, the strange openness disappears into an ordinary result. You never witness a broken timeline spreading through the room. You see only the quiet evidence that, before the record became fixed, nature completed the task without traveling along a single road. A quantum object's property can appear where the object itself is not. A neutron enters a device through two possible corridors. Yet when scientists gently search for the neutron in one corridor and its magnetism in the other, the instruments respond as though the object and one of its defining properties have taken different routes. This phenomenon is known as the quantum Cheshire cat, named after the creature whose grin remained visible after the rest of its body disappeared. In a well-known experiment, neutrons were sent through a crystal interferometer that divided their quantum state between two paths. The neutron spin, which gives rise to its magnetic behavior, was prepared in a carefully controlled way, and only neutrons matching a chosen final condition were included in the results. Between the preparation and the final detection, the researchers used weak measurements, interactions so gentle that they revealed only tiny statistical shifts across many repeated trials, rather than forcefully determining the state of each individual neutron. When a weak absorber was placed in one path, the detected intensity changed as though the neutron had traveled there. But when a weak magnetic field was applied, the response associated with the neutron's spin appeared mainly in the opposite path. The measurements therefore produced a pattern consistent with saying that the neutron passed through one arm while its magnetic moment passed through the other. A later photon experiment reported a related effect in which the photon's location and its polarization produced separated weak measurement signatures. Yet the careful phrase is "behaved as though" because the experiment did not photograph a naked property floating through space without its particle. Weak measurements describe conditioned patterns collected from an ensemble that has been both prepared and selected in particular ways. Physicists continue to debate whether those patterns should be interpreted as the literal location of the particle and its property, as optimal estimates based on the selected data, or as interference between quantum possibilities that cannot be translated into a simple story about one definite journey. Some modern analyses argue that the Cheshire Cat effect reveals contextual quantum coherence, rather than proving that a physical attribute has truly detached from its owner. This distinction does not make the result ordinary. It reveals something more precise and perhaps more unsettling. At the quantum level, a property is not always a tiny possession carried around like a coin in a pocket. Spin, polarization, and other measurable qualities are expressed through the full relationship between preparation, possible paths, interactions, and final detection. Change that experimental context, and the meaningful location of the property can change with it. In everyday life, redness remains with the apple, warmth remains with the flame, and a smile remains on a face because large objects constantly interact with their surroundings, producing stable combinations of objects and attributes. Quantum systems are not required to preserve that familiar picture. Their properties may be distributed through patterns of possibility that only become visible through carefully chosen interactions. So the lesson of the quantum Cheshire Cat is not that nature contains invisible smiles wandering alone through laboratories. It is that the bond between a thing and what you say belongs to it may be less fundamental than it appears. Beneath the calm surface of ordinary matter, an object may not be a container filled with permanent qualities, but part of a wider arrangement in which the path, the property, and the question used to examine them help define one another. The universe may not always decide whether A caused B or B caused A. Place two sealed laboratories far from one another and call them A and B. Inside each laboratory, a researcher receives a physical system, performs a freely chosen operation, and records an outcome. But neither researcher is told whether their action belongs earlier or later in the larger process. In an ordinary causal world, only a few explanations are available. A may act first and influence B. B may act first and influence A. Or the laboratories may be arranged so that neither can affect the other. Even when the order is hidden, you assume that one of these structures must secretly be true. A framework called the process matrix formalism asks what quantum theory predicts when that assumption is removed. It keeps the ordinary rules of quantum mechanics inside each local laboratory, but does not begin with a single global timeline connecting them. When researchers study the correlations allowed by this framework, they find theoretical processes that cannot be explained as A causing B, B causing A, or an ordinary probabilistic mixture of both directions. The data can violate constraints known as causal inequalities, which are rules that every process with a definite causal order must obey. This does not mean that an event simply creates itself or that the universe permits contradictions. The framework is constructed so that the probabilities remain consistent and the observers do not obtain impossible outcomes, such as a result that prevents the very conditions producing it. What disappears is not logic, but the demand for one universal answer to the question of causal direction. A and B may participate in a larger quantum relationship, whose correlations cannot be assembled from the classical stories of first and B first. There is also an important scientific boundary here. A process can be causally non-separable, meaning it cannot be decomposed into fixed orders, without necessarily producing correlations that violate a causal inequality. Detecting unusual causal structure is therefore not always the same as proving the strongest form of causally indefinite behavior, and physicists continue to study which mathematically permitted processes can be physically created in nature. No such result allows you to telephone your earlier self, prevent your own experiment, or send information through a paradoxical loop. The mystery concerns the architecture connecting local events, not a machine for rewriting yesterday. This matters because causation is usually treated as more fundamental than the objects it organizes. You expect the universe to carry an invisible ledger in which every influence has a source, every consequence has a predecessor, and every pair of connected events can eventually be placed in the correct direction. Quantum theory suggests that this ledger may not exist at the deepest level in the form you imagine. A definite causal order may emerge only when delicate quantum relationships lose their coherence and become embedded in the stable, large-scale world. The classical limit of the original framework restores ordinary causal structure, hinting that the direction you experience so naturally may be a reliable macroscopic pattern rather than an indivisible ingredient of reality. You still live in a world where sparks ignite fires and footsteps leave prints, but those familiar sequences may be the settled surface of something less rigid underneath. Perhaps the universe does not always begin by choosing which event commands and which event obeys. Perhaps, in its smallest and quietest processes, it first permits a relationship that has no single direction, and only later allows the flowing world you know to arrange that relationship into a story with a beginning, a consequence, and an arrow pointing forward. A measurement result may exist inside a laboratory but not outside it. The strangest object in a sealed quantum laboratory may not be the particle being measured, but the sentence written afterward. The result was 1. Inside the room, that sentence can feel as final as any ordinary fact. A detector responds, information enters a memory, and the observer can use the result to predict what they will see next. Yet, an external physicist who treats the entire isolated room according to quantum theory may be unable to assign that record a single definite value. The reason lies in what measurement physically does. A detector does not pull an answer from nowhere. It becomes correlated with the system. One possible particle state becomes connected to one detector reading, while another state becomes connected to a different reading. The observer's memory can then join the same chain. From inside each resulting branch of this correlation, the observer possesses one clear record and never experiences a vague mixture of answers. From outside, however, the complete laboratory can still be described by a quantum state containing all the correlated alternatives, provided nothing has leaked into the environment. The outside scientist may even choose a special measurement designed not to read the internal notebook, but to test whether coherence still exists between the possible laboratory histories. If that interference can be detected, then the external description cannot simply replace the laboratory with one unknown but already settled outcome. The internal record behaves as a fact for the observer who holds it, while for the outside experiment, it remains part of a reversible quantum process. This is where the problem becomes more than a disagreement caused by missing information. Suppose you secretly place a coin in a box. Someone outside may not know whether it shows heads or tails, but everyone assumes that one answer already exists. In the quantum laboratory, the external observer's uncertainty can be structurally different. The theory may require the alternatives to remain coherent rather than merely concealed. A sufficiently controlled external operation could recombine them, and doing so might disturb or even alter the memory that once stored the internal result. Research on Wigner's friend scenarios has shown how difficult it is to maintain. The idea that an observer's recorded perception persists as one absolute fact while the entire laboratory continues through fully reversible quantum evolution. Under certain combinations of assumptions, the observer's earlier and later records cannot be treated as values belonging to one ordinary joint history. None of this means that scientists can currently place a conscious human in an isolated chamber and erase a remembered experiment. Real laboratories constantly release heat, light, vibrations, and information into their surroundings, causing delicate coherence to disappear extraordinarily quickly. Proof of principle tests therefore use photons, paths, detectors, or other small systems as simplified models of observers and records. Such experiments place restrictions on the belief that all observed events must possess one observer-independent existence. But their conclusions depend on assumptions about locality, freedom of measurement choices, and the universal applicability of quantum evolution. The deeper lesson is that a measurement result may not begin as a public inscription carved into the universe. It may begin as a correlation stored within a particular physical relationship, real enough to guide the observer inside, yet not available as a single settled fact to every possible description outside. Only when the record escapes the room, spreads through the environment, and becomes copied into many places does it acquire the durable public character you normally associate with reality. You live surrounded by such copied records, photographs, memories, scars, sounds, and traces that agree with one another so overwhelmingly that the world appears to have only one history. But the sealed quantum laboratory suggests that beneath this shared surface, a fact may first belong to the place where it was formed, waiting for the wider universe to receive it before it becomes a fact for everyone. Reality may change. When the observer is placed in quantum superposition, picture an observer standing on a platform that has not been placed at one definite location, but has been prepared in a delicate quantum combination of two separated positions. From the perspective of a larger laboratory, the platform occupies both alternatives coherently, and everything attached to it serves as a reference frame whose location is not classically fixed. It is tempting to imagine that the observer on the platform would look down and see two floors, two instruments, or two versions of the room layered over each other, but that is not what the theory says. When physicists change into the reference frame of the quantum platform, the platform itself can be treated as resting at one definite origin. What changes is the description of everything around it. The external laboratory that previously regarded itself as stationary may now be represented in a superposition of positions relative to the platform. An object that appeared independent of the observer from the outside may become entangled with the external laboratory when described from the platform's frame. Conversely, two systems that looked entangled from the first viewpoint can appear separated from the second. Quantum reference frame theory was developed to describe transformations of this kind without assuming that one classical laboratory possesses an absolute view of the world. It shows that superposition and entanglement can depend on which physical system is chosen as the reference frame, even though properly calculated experimental probabilities remain consistent between the descriptions. Consider a simpler image. From a station, you say that a train is moving while the platform is still. From the train, you say that the platform moves backward while your seat remains still. Classical relativity already teaches you that motion belongs to relationships rather than objects in isolation. The quantum version goes further because the train itself may follow more than one coherent position or velocity at once. Changing perspective is then no longer one ordinary shift of coordinates. It becomes a coordinated transformation associated with each branch of the reference frame's quantum state. This can move the appearance of superposition from one system to another and change how the total world is divided into apparently independent parts. More recent work has clarified why even the notions of the same position in two branches or different positions in two branches require a chosen quantum frame to identify which configurations are being compared. In that sense, sameness, separation, and entanglement may lose the absolute meanings they possess in everyday space. This does not imply that consciousness reshapes matter, or that an observer can select a preferred reality through attention. The observer may be an atom, a clock, a small platform, or another physical system used to define distances and motion. Nor do the transformations produce conflicting detector statistics. They reorganize the relational description while preserving what observers can ultimately compare through physical communication. The insight is subtler. When the ruler used to describe the universe becomes quantum, some properties you assumed belong to objects alone reveal their dependence on that ruler. An object may be spread out relative to one frame and localized relative to another. A pair may be entangled from one perspective and unentangled from another, because the boundary separating the systems has changed with the frame. Reality does not dissolve into arbitrary stories. Instead, it becomes more relational than the classical world taught you to expect. You have always measured position from somewhere, motion against something, and distance between physical bodies. Quantum reference frames ask you to notice that the somewhere is itself made of matter and must therefore obey the same uncertain laws as everything it observes. Once the observer is allowed to enter superposition, the universe does not lose its rules. It quietly reveals that the stage from which reality is described was never outside the play. An effect may occur before and after its cause at the same time. A device sits on a laboratory table with one opening marked as the entrance and another marked as the exit, yet a photon approaches it in a way that prevents nature from assigning either opening one permanent role. In ordinary experiments, information enters a device, undergoes a transformation, and leaves afterward. Even when you do not understand what happens inside, the direction remains clear. The input belongs to the beginning, and the output belongs to the end. Quantum researchers have now explored a stranger possibility called the quantum time flip, in which a single process is examined in a coherent combination of its forward and time reverse directions. In one part of the quantum description, the device receives the photon through what you would normally call its input and produces an output. In the other, the roles are reversed, so the same transformation is probed in the opposite input-output direction. These possibilities are not selected like two hidden routes in a lottery. They are kept coherent, allowing their probability amplitudes to interfere before a final measurement is made. In that carefully controlled sense, what serves as an effect in one direction occupies the position of a cause in the other, and the experiment does not begin with one definite answer about which orientation is real. This is different from placing two separate operations in an uncertain order. Here, the mystery belongs to the direction through one operation itself. The distinction between entering and leaving becomes part of the quantum state. In 2024, researchers demonstrated this input-output indefiniteness with photonic systems and found statistical evidence that the observed process could not be reproduced by merely choosing a definite direction at random. Another experiment implemented a quantum time flip and used it to perform a discrimination task more successfully than strategies restricted to one fixed time direction. Yet this does not mean that a detector flashes before anyone builds it, that a shattered glass repairs itself, or that information travels into the human past. The experiment does not reverse the thermodynamic history of the laboratory, and no observer receives a message before it is sent. The phrase backward direction refers to how an allowed quantum transformation is accessed and connected to its inputs and outputs, not to an entire macroscopic world running backward. Many microscopic laws are compatible with time reversal, even though the large world around you displays a strong arrow from ordered pasts toward less ordered futures. The quantum time flip takes advantage of that microscopic flexibility without abolishing the ordinary sequence of your memories. Its importance lies in revealing that the architecture used to probe a process can possess possibilities unavailable to any classical circuit with a permanently assigned entrance and exit. A quantum device may therefore extract information not by repeating a process twice, but by allowing forward and reverse descriptions to participate in one experiment. The final detector still records an ordinary result, but that result carries an interference pattern formed from two incompatible temporal orientations. You may picture causation as a river whose water can only be studied while flowing downstream. Quantum physics suggests that, for certain tiny and highly controlled transformations, nature can compare downstream and upstream descriptions without committing to either one alone. By the time the answer reaches you, time appears calm and directional again. But hidden inside that answer is evidence that the universe may sometimes complete a process before deciding which side deserved to be called the beginning. A particle can travel along one path while its spin appears along another. Watch a beam of neutrons enter a perfect crystal and split into separate paths. And you might assume that every neutron must carry its spin along whichever route contains the particle, just as a turning compass needle must remain attached to the compass. Neutron interferometry challenges that comfortable picture because a neutron's path and its spin are different parts of one quantum state, and carefully arranged interference can make them respond as though they occupy different regions. In the original neutron quantum Cheshire Cat experiment, researchers first prepared the neutrons so that their paths were correlated with particular spin orientations. After the paths were separated inside a silicon interferometer, only neutrons passing a carefully chosen final test were counted. This preparation and final selection created a special sub-ensemble in which local disturbances produced an extraordinary pattern. A weak absorber inserted into one path reduced the final neutron count, indicating that the particle population was associated mainly with that route. But a small magnetic field, which acts on spin rather than simply blocking particles, produced its strongest signature when placed in the other path. The experiment therefore behaved as though the neutron traveled through one arm while a component of its magnetic moment appeared in the other. The instruments did not catch a free piece of spin floating by itself. Spin is not a substance that can be scraped from a neutron and stored in an empty box. It is a quantum degree of freedom describing how the neutron responds to magnetic interactions. What the experiment separated were the locations at which two different kinds of weak disturbance affected a specially prepared and post-selected interference pattern. The neutron's presence was inferred by gently changing the intensity along each path, while the spin's apparent location was inferred by observing how local magnetic rotations changed the final signal. Because these interactions were weak, no single neutron announced a complete route and spin history. The conclusion emerged statistically after the experiment had been repeated many times. This is essential because a strong attempt to determine exactly which path each neutron followed would destroy the interference that makes the effect possible. Researchers still disagree about how literally the results should be described. Some regard the weak values as meaningful evidence that the particle and its property can be spatially disembodied within the selected ensemble. Others argue that the apparent separation is better understood as interference between transition amplitudes, shaped by the initial preparation, the local disturbances, and the final filter, rather than by two independent entities traveling through the apparatus. Later work clarified that the Cheshire Cat pattern can arise from cross-terms between amplitudes, and a three-path neutron experiment extended the method by making the neutron's path, spin, and energy respond in different arms, while also emphasizing that no universal interpretation has been accepted. This debate does not erase the measured effect. It tells you precisely where the mystery lives. The data show that asking where the neutron influenced the apparatus and asking where its spin influenced the apparatus need not produce the same spatial answer. What remains unsettled is whether those answers describe literal journeys or only the relational structure of a quantum transition. In the world you touch, properties seem securely fastened to objects because countless environmental interactions continually reinforce that arrangement. Inside an isolated interferometer, however, nature answers more delicately. It may place the trace of matter in one corridor and the response associated with spin in another, not because the neutron has broken into pieces, but because the complete quantum event cannot always be reduced to the path of a tiny object carrying a fixed bag of attributes. The neutron leaves the apparatus whole, yet the evidence it leaves behind quietly asks whether a property truly belongs to an object at every moment, or whether belonging itself is something that becomes definite only when the experiment forces the two back together. Two observers can make correct predictions while describing different realities. One observer can predict certainty while another predicts pure chance, and quantum physics allows both of them to be correct. Imagine that Alice prepares a series of photons, choosing either vertical or horizontal polarization for each one, while Bob receives the photons without being told which choice she made. For Alice, every photon has a precisely known preparation, so if Bob measures in the matching way, she can predict each individual result with certainty. Bob, however, possesses no record of her choices. Before receiving her message, the most accurate description available to him assigns equal probabilities to the two results. When many photons are tested, Alice's conditional predictions are correct for every preparation, while Bob's 50-50 prediction is correct for the collection as a whole. They have not discovered two contradictory laws of nature, and Bob is not simply being careless. A quantum state is partly a tool for organizing what a physical observer can predict from the information available to them. Different records can therefore justify different state assignments to the same system. This becomes more profound in relational interpretations of quantum mechanics, where the state of a system is not treated as an absolute label carried through the universe. Instead, it describes the relation between that system and another physical system that has interacted with it. A property may be definite relative to one observer, while remaining indefinite relative to another that has not shared the relevant interaction. Carlo Rovelli originally developed this idea by arguing that quantum theory may not require observer-independent states or observer-independent values for every physical quantity. Yet this is an interpretation of the theory, not a universally accepted experimental conclusion, and researchers continue to debate whether all versions of relative facts remain consistent when several observers and measurements are combined. The crucial restriction is that observers are not free to describe anything they please. Each description must correctly predict the outcomes accessible from that observer's physical situation, and when new information arrives, the assigned state must change accordingly. Once Alice tells Bob how each photon was prepared, his uncertainty disappears, and his new predictions agree with hers. Quantum mechanics preserves this agreement through correlations. It does not leave them trapped forever in private worlds that can never meet. What changes is the idea that there must have been one complete description available from nowhere in particular, a view belonging to no observer and containing every fact simultaneously. You are accustomed to thinking of knowledge as an imperfect copy of a reality that is already fully written. Quantum theory invites a quieter possibility. Perhaps a description becomes meaningful only from a position within the physical world, connected to particular records, interactions, and questions. Two observers may then carry different but equally valid maps, not because truth has vanished, but because neither map was drawn from outside the universe. And when they finally exchange what they know, reality does not need to choose which observer had been wrong. It simply reveals the larger pattern in which both predictions had their proper place. A quantum operation can pass through two opposite orders simultaneously. Single photon can enter two unknown operations and return carrying information that no ordinary fixed-order circuit could obtain while using each operation only once. This becomes possible because quantum mechanics can place not only particles and paths into superposition, but also the sequence of instructions applied to a system. The device that performs this task is called a quantum switch, but its most revealing feature is not that it changes from one order to another. An ordinary switch could already choose operation A, followed by operation B on one trial and reverse them on the next. The quantum version uses a control system prepared coherently so that one alternative sends a target through A and then B, while the other sends it through B and then A. The alternatives remain capable of interference, meaning the experiment retains the phase relationship between the two opposite sequences. In optical demonstrations, a photon's path can act as the control, while another property, such as its polarization, carries the information being processed. Along one route, the polarization encounters the gates in one order. Along the other route, it encounters the same gates in reverse. The paths are then recombined, and the photon's exit reveals something about the relationship between the two operations. This allows researchers to solve a particularly elegant problem. Two unknown gates are promised either to behave identically regardless of which one acts first, or to produce a sign change when their order is reversed. With a conventional fixed-order circuit, using each unknown gate only once is not enough to distinguish these cases perfectly. In the quantum switch, both sequences contribute to the final interference, so the control system can reveal whether reversing the order changed the transformation. A photonic experiment demonstrated this task with each gate used once and achieved a success rate exceeding the best possible fixed-order strategy under the same restriction. This is an example of a higher-order quantum operation. Rather than merely transforming a state, it accepts other transformations as its inputs and controls how they are connected. That distinction opens a new layer of quantum computation. A normal circuit treats its wiring diagram as fixed before the experiment begins, even when the information traveling through it is uncertain. A quantum switch makes part of the wiring itself coherent and allows different circuit structures to interfere. Later experiments have certified photonic implementations using causal witnesses and have shown that the observed process cannot be represented as an ordinary mixture in which one definite order secretly occurred on every trial. The result does not mean that the photon is copied, that the gates act without physical interactions, or that a computer receives an answer before performing its calculation. Nor does every task become faster simply because the order is quantum. The advantage appears only for particular problems that can use the interference between sequences. What changes is the status of order itself. In everyday machines, instructions are written on a rigid timeline. First, do this, then do that. Here, the timeline of the instructions becomes part of the information being processed. Nature allows the system to explore two opposite compositions without reducing them to two separate experiments, and the final measurement extracts a feature that exists in their relationship. You might think of a sequence as an invisible container that events must enter one by one. Quantum physics suggests that, under delicate conditions, the container can also become a variable. The operations remain real, the laboratory clock still advances, and one detector eventually produces one result. Yet the answer carries the imprint of two incompatible routes through the logic of the machine. For a brief interval, the universe does not merely process information in time, it processes the order of time as information. The direction of time through a quantum process may be indefinite. Entropy usually gives you a reliable way to tell which side of an event belongs to the past. Perfume spreads through a room, but does not spontaneously return to its bottle. Heat flows from a warmer object toward a colder one, and a shuffled deck does not naturally rebuild its original order. These changes define the thermodynamic arrow of time, the direction in which disorder and lost information generally increase. Yet the microscopic laws controlling atoms and particles are largely compatible with both forward evolution and its time-reversed counterpart, creating a deep question about where the familiar direction of time truly begins. Quantum theory introduces an even stranger possibility. A sufficiently isolated system can be prepared so that a forward thermodynamic process and its reversed version contribute coherently to the same evolution. In the forward alternative, the system moves from a less probable state toward equilibrium and produces positive entropy. In the reversed alternative, it follows the corresponding sequence backward, appearing to recover order and produce negative entropy. A classical experiment could randomly choose one direction or the other, but each trial would still possess a hidden, definite arrow. A quantum superposition preserves a relationship between the two alternatives, allowing them to interfere rather than behave like separate histories. Theoretical work on opposing thermodynamic arrows shows that this interference can create patterns of entropy production that no ordinary mixture of forward and backward processes can reproduce. When the measured entropy change is large, the result effectively reveals one direction and the familiar arrow returns. When the change is small, however, the two temporal alternatives can remain difficult to distinguish, and their amplitudes may combine to make the evolution appear more reversible or less reversible than either direction would appear alone. This does not mean that a warm cup can cool and heat itself simultaneously in your kitchen, or that a person could remember tomorrow while forgetting yesterday. Macroscopic systems continuously exchange information with enormous environments, destroying the coherence required to combine opposing arrows. The idea concerns carefully controlled quantum processes, in which the distinction between a forward transformation and its time reverse has not yet become an irreversible record. A broader framework for operations with indefinite time direction also shows that certain quantum devices can, in principle, be used in coherent combinations of forward and backward orientations, producing information processing abilities unavailable to procedures restricted to one definite direction. These operations remain theoretical in their most general form, and their physical accessibility may be limited by principles not yet understood. What they reveal is not that time has stopped, but that the arrow you experience may not be written into every microscopic event from the beginning. It may emerge when information spreads, alternatives lose their ability to interfere, and one direction becomes preserved in records that cannot practically be undone. You remember the past because traces of it surround you, while the future has left no comparable archive. But before such traces are formed, a quantum process may contain no single answer to the question of which temporal orientation it followed. The direction of time may begin not as a road already laid beneath reality, but as a distinction that becomes sharper each time the universe allows information to escape and refuses to gather it back. Quantum theory may be unable to describe every observer's experience at once. 4 scientists follow the rules of quantum mechanics perfectly, yet after combining what each of them claims to know, they can arrive at a conclusion that the same theory says should be impossible. This is the unsettling core of the Frauchiger-Renner thought experiment, which was designed not to test an ordinary particle, but to test whether quantum theory can consistently describe agents who are themselves using quantum theory. The scenario begins with an observer making a quantum-controlled choice and using the result to prepare a second system. Another observer measures that system inside a separate sealed laboratory. Later, 2 external experimenters perform measurements on the laboratories as complete quantum objects, rather than simply opening the doors and asking what happened. Each participant uses their own result and the standard rules of quantum prediction to infer what another participant must have observed. One conclusion implies another, which implies another, until a chain of statements appears to establish with certainty that a particular final outcome cannot occur. Quantum theory nevertheless assigns that outcome a real non-zero probability. If the procedure is repeated enough times, the forbidden-looking combination should eventually appear. The contradiction does not arise because anyone calculated carelessly. It arises when several individually valid predictions, made from different observational positions, are treated as pieces of one ordinary history in which all agents' certainty statements can be combined without restriction. Frauchiger and Renner argued that 3 attractive principles cannot all remain untouched. Quantum theory applies universally. Every measurement has one single outcome, and different agents can consistently adopt one another's certain conclusions. Abandoning universal quantum theory would mean that observers or laboratories eventually stop obeying the same rules as microscopic systems. Abandoning single outcomes would allow different results to persist in separate branches, as in many worlds interpretations. Restricting consistency would mean that a statement certain for one observer cannot always be imported into another observer's description, as though both belong to one shared viewpoint. None of these options is comfortable, and this is why the thought experiment remains debated. Some researchers argue that the contradiction results from combining incompatible descriptions or from failing to include the complete physical situation, while other work has reformulated and strengthened the puzzle by connecting it to quantum contextuality, the fact that outcomes cannot always be assigned independently of the measurement setting in which they appear. No human being has been placed into the required perfectly isolated laboratory, and the experiment does not prove that real scientists experience logical contradictions in everyday life. Its force is conceptual. If observers, memories, measuring devices, and reasoning processes are all physical, then a universal theory should presumably be able to describe them together. Frauschige-Renner shows that the straightforward method of giving each observer an ordinary single experience while allowing every other observer to model that entire experience quantum mechanically may not fit into one seamless account. Quantum theory remains extraordinarily successful at predicting observed statistics, but it may resist becoming a single view from nowhere that contains every observer's private certainty at once. Perhaps the universe permits each perspective to be locally coherent, while denying you the ability to combine all perspectives into one classical story. And perhaps what fails is not reality itself, but the quiet assumption that every truth known from within the world must also fit unchanged into one final description written from outside it. A particle can leave a trace in a region. It was never definitively inside. A mirror trembles by an almost unimaginable amount, and from that tiny vibration, physicists infer that a photon somehow touched a region where no ordinary path can confidently place it. This puzzle emerges in nested interferometers, devices containing several possible routes arranged so that waves of light can cancel one another in carefully chosen places. In a famous experiment, several mirrors were made to vibrate at different frequencies, giving each route a faint identifying mark. Photons traveled through the apparatus and were detected only at one selected output, after which researchers searched the final beam for the frequencies associated with the mirrors. Some mirror signatures appeared exactly where a continuous trajectory would suggest, but others emerged in an apparently disconnected part of the interferometer, while the expected traces at the entrance and exit of that region were strongly suppressed. It was as though the photon had left fingerprints inside a room without clearly passing through either doorway. The experiment's authors argued that a quantum particle's past should be defined by the places where it leaves weak physical traces, rather than by a single uninterrupted path imagined after detection. These traces were not complete footprints left by individual photons. Each mirror caused only a minute change, and the pattern became visible after many detection events were combined. The result, therefore, describes the statistical history of a carefully prepared and selected group of photons, not a camera recording one particle jumping into an isolated region. The interpretation remains disputed. Other analyses show that different measurement methods or different frameworks for assigning quantum histories can produce a more continuous account, and critics warn that a weak signal does not automatically prove that a particle was literally present in the everyday sense. Some approaches treat the detected frequencies as interference information carried by the entire wave through the apparatus, rather than as location labels attached to a tiny traveler. Yet the disagreement itself teaches something important. Before measurement, the question, "Where was the particle?" may not possess the same kind of answer as "Where was the stone?" A stone can usually be assigned a continuous route because its interactions with the environment constantly record its position. A photon inside a protected interferometer is described by amplitudes spread across possible paths, and those alternatives can cancel at one point while still influencing a later result. A region may therefore contribute to the final detection and retain a measurable trace, even when no consistent classical story says that the photon definitely entered, crossed, and left it. The particle has not teleported, traveled backward, or appeared from nothing. Rather, the experiment reveals that influence and definite presence are not always identical concepts in quantum physics. You may search for a neat line connecting source and detector, but nature sometimes answers with scattered evidence instead, leaving you to wonder whether the past is a route that existed before you looked or a pattern reconstructed from the traces that survived. The boundary between two objects may change. With the observer's reference frame, two quantum objects can be separate from one perspective, yet fail to divide into the same two independent pieces from another, not because their material surfaces have moved, but because the meaning of a subsystem can depend on the physical frame used to describe it. In ordinary life, dividing the world seems effortless. The clock is one object, the table is another, and the wall between them appears to settle the matter. Quantum theory, however, describes systems through the properties that can be measured independently and through the correlations connecting those properties. When a reference frame is itself treated as a quantum object, changing from one frame to another can reorganize those measurable relationships. Imagine three particles floating with no external grid telling you where absolute space begins. You may choose the first particle as your origin and describe the other two by their distances and motions relative to it. From this viewpoint, certain variables belong naturally to one object and others to another. If you instead adopt the second particle as the frame, the new relational variables can combine information that was previously assigned to separate parts. The total physical situation has not changed, but the most natural division into independently describable subsystems may have. Research on the quantum relativity of subsystems shows that different quantum reference frame perspectives can generate different collections of observables for the supposed parts of a composite system. Degrees of freedom that behaved like independent subsystems in one perspective may become intertwined in another, and even the mathematical notion of locality, whether two sets of operations belong to distinct parts, can become frame-dependent. This goes beyond saying that two observers merely use different coordinates. A classical change of coordinates moves labels while preserving the same obvious objects underneath. A quantum frame transformation can alter how the total state is factorized into parts, because the system chosen as the new frame is placed in a definite relational condition, while quantum uncertainty is transferred into the description of what surrounds it. Closely related work has shown that judgments such as whether two configurations are the same across different branches, and therefore whether certain systems count as entangled, depend on which quantum frame is used to compare them. None of this means that an observer can stare at two atoms and physically fuse them, or that a laboratory wall disappears when someone changes perspective. The boundary being questioned is not a visible edge. It is the deeper theoretical boundary that tells you which quantities belong to which independently describable object. All observers must still agree on relational predictions when they correctly translate between frames. What changes is the assumption that nature arrives already divided into one unique collection of pieces. Perhaps objects are stable patterns that emerge because certain relationships remain reliable, while the most fundamental description belongs not to isolated things, but to the connections from which their apparent separateness is built. You look at the world and see objects first, with relationships stretched between them afterward. Quantum reference frames suggest that, at a deeper level, the relationships may come first, and the boundaries may be what the chosen observer draws from within them. A quantum experiment may work better because its steps have no fixed order. A message can become dramatically shorter, not because it has been compressed, but because nature refuses to decide which direction it traveled first. This possibility appears in quantum communication tasks, where two distant participants receive private pieces of information and must determine a property that depends on both inputs while exchanging as little physical information as possible. In any protocol with a fixed direction, one participant must act as the sender and the other as the receiver, so the message must contain enough detail to work regardless of which hidden input the receiver possesses. As the size of the problem grows, the required communication can become enormous. A quantum protocol can change the structure of the task by placing the direction of communication into a coherent combination. Along one alternative, information travels from Alice to Bob. Along the other, it travels from Bob to Alice. These are not two separate attempts chosen by a hidden coin toss, because the two directions retain a quantum relationship and are recombined before the final answer is read. The useful information is encoded not only in what traveled, but in how the opposite communication histories interfere. In a photonic experiment, researchers implemented this idea with high-dimensional quantum systems and tested a distributed computation problem designed to reveal the difference between fixed and indefinite direction. As the dimension increased, the quantum switching protocol used substantially less communication than any protocol restricted to one causal direction, with the largest demonstration requiring only about 70% of the information demanded by the best fixed-order strategy under the same conditions. The underlying theory predicts that the gap can grow exponentially for larger versions of the task. This advantage does not arise because the photon carries an unlimited amount of hidden data, or visits both laboratories as two independent copies. One quantum system is exchanged, and each participant performs a controlled operation determined by their private input. What changes is the route through which those operations are connected. A classical protocol must decide the communication structure before the unknown inputs are fully combined, while the quantum procedure lets two opposite structures contribute to one final measurement. That difference can reveal a global feature of the inputs without transmitting enough information to describe them individually. It is important not to turn this result into a promise that every quantum experiment becomes faster when its order is uncertain. The advantage belongs to specially constructed problems, and imperfections can erase it if the two alternatives lose coherence. Many ordinary tasks gain nothing from indefinite order, while some apparent advantages can be reproduced by fixed circuits if they are allowed extra uses of the operations. Yet research has also shown that reproducing the complete action of a quantum switch on general unknown channels may require a fixed-order circuit to call those channels vastly more times, demonstrating that the resource cannot always be reduced to clever rewiring. The lesson is subtle but powerful. Efficiency does not depend only on the operations available to nature, but also on whether their arrangement must be settled in advance. You normally think that a task is defined by a list of steps, and that improvement means performing those steps more quickly. Quantum physics suggests another possibility. Sometimes the deeper limitation is the list itself, and the experiment succeeds not by rushing through one sequence, but by refusing to live inside a single sequence until the answer has already begun to form. Two observers may disagree about whether the same object is entangled. Entanglement can disappear without any interaction breaking it, simply because the observer changes the physical system from which the universe is being described. To understand how this can happen, imagine three quantum objects floating in space with no perfectly fixed external grid behind them. One object serves as a reference frame, while the other two are described by their positions relative to it. From this perspective, the two observed objects may possess a joint state that cannot be separated into independent descriptions. Measuring one can then provide information about the other, so the observer identifies them as entangled. Now replace the original reference frame with one of the quantum objects being observed. This is not an ordinary change of viewpoint like walking around a table, because the new frame may itself have been spread across several positions relative to the old one. Moving into its perspective requires a quantum transformation that redistributes uncertainty and correlations throughout the complete system. The new observer treats their own frame as localized, while the former reference frame may now appear in a superposition. After this transformation, correlations that previously connected the two observed objects can be transferred into relationships involving the old frame, and a pair that appeared entangled before may now possess a separable description. The reverse can also occur. Objects described independently in one frame may become entangled in another. Quantum reference frame theory demonstrates mathematically that superposition and entanglement can be frame-dependent in this way. This does not mean that entanglement is an illusion or that two observers can obtain genuinely contradictory laboratory results. Entanglement remains a measurable resource, capable of producing correlations impossible for ordinary classical systems. But identifying where that resource resides requires a choice about which degrees of freedom count as the systems on which physical object defines the frame. When observers translate not only the state but also their measuring instruments and questions into one another's frames, they predict compatible outcome statistics. Their disagreement concerns the internal description used to organize those predictions, not what happens when their records are finally compared. You can think of a familiar knot tied between two ropes. In classical life, changing your position does not untie it because the ropes remain clearly identifiable objects. In a quantum system, however, changing frames can alter which relational variables function as the ropes. The correlation does not vanish from the total physical state. It may be reassigned from one division of the world to another. This matters because entanglement is often spoken of as though it were a permanent substance stored between two particles. In reality, it is a property of a state relative to a chosen way of dividing and describing the system. Quantum frames reveal that even this division can belong to physics rather than to an invisible, absolute stage. No conscious decision creates or destroys the connection, and no observer gains the power to transmit a message by choosing a convenient perspective. The observer here can be an atom, a clock, or any physical system used to define position and motion. What changes is the relational map through which correlations are identified. Two observers may therefore disagree honestly about whether a particular pair is entangled while still agreeing on every experiment they can compare. The bond has not been broken. It has been located differently, and beneath that quiet shift lies a profound question. Perhaps the universe does not contain entanglement in isolated places waiting to be discovered, but contains one web of relations whose apparent knots depend partly on where within the web you begin to look. A quantum system can contain energy that exists but cannot be extracted as work. A quantum battery can be full of energy and still be unable to power anything, because possessing energy is not the same as having energy arranged in a usable form. Imagine a small system with several energy levels, like shelves placed at different heights. If too much population sits on the upper shelves while lower ones remain relatively empty, a controlled operation can rearrange those populations, lower the system's average energy, and transfer the difference into a battery, a field, or another work storage device. Quantum thermodynamics calls the maximum energy obtainable through an ideal cyclic control process the system's ergotropy. But once the populations have been arranged so that the most occupied states already sit at the lowest energies, no further energy can be removed by such a reversible rearrangement. The system has entered what physicists call a passive state. It may still contain a large amount of internal energy, yet every allowed cyclic transformation would leave its average energy unchanged or make it higher. The energy has not vanished. It remains physically present, contributing to the system's temperature and internal motion, but it is no longer accessible as ordered work under the chosen rules. This is similar to standing beside an enormous lake whose surface is perfectly level. The water possesses energy, but without a height difference, there is no downhill flow to turn a turbine. In a quantum system, the missing slope is not necessarily spatial. It is the absence of a useful imbalance among energy levels. Coherence can complicate this picture, because a state may contain delicate phase relationships between its energy levels, and those relationships can sometimes provide extractable work even when there is no obvious population inversion. After the usable population imbalance and coherence have been exhausted, however, energy can remain trapped in the passive remainder. Researchers studying quantum batteries describe this residual portion as energy that is stored but unavailable through unitary work extraction protocols, and recent many-body results show that even highly energetic pure states may yield almost no useful work when only realistic finite-time operations are allowed. There is an additional twist. Some states that are passive on their own can become active when several copies are combined, because collective operations reveal imbalances invisible in each individual copy. Thermal equilibrium states are exceptional. They are completely passive, meaning that no number of identical copies can be combined to produce work through an ideal cyclic rearrangement. So when you hear that a system contains a certain amount of energy, you still do not know how useful that energy is. You must also ask how it is distributed, what control you possess, what information you have about the state, and whether you are allowed to manipulate the system globally or only in limited ways. Energy is a quantity, but work is an opportunity. A quantum system can hold the first long after the second has disappeared, quietly reminding you that nature does not measure value by how much something contains, but by whether there remains a physical path through which that stored possibility can be released. Repeated measurement can create an entirely new phase of matter. Physicists can drive a quantum system through a phase transition without heating it, cooling it, squeezing it, or changing the forces between its particles. Sometimes, all that is required is to change how often the system is observed. Consider a chain of qubits evolving under interactions that continually spread quantum information. Left alone, these interactions scramble the initial state and build entanglement across increasingly large distances, so that learning the full condition of one region requires understanding much of the rest of the system. Now interrupt this evolution with repeated local measurements. Each measurement forces one small part of the system into a recorded outcome and removes some of its uncertainty, cutting through portions of the growing entanglement network. Two opposing tendencies are now competing. The internal dynamics tries to hide information in complex correlations distributed across the entire system, while measurement continually exposes local information and breaks some of those correlations apart. When measurements are rare, the scrambling wins. The system enters a highly entangled regime in which the amount of entanglement associated with a region grows roughly with the size of that region. When measurements occur frequently enough, they win instead, preventing long-range entanglement from surviving and producing a regime in which the entanglement is concentrated mainly near the region's boundary. Between these behaviors lies a critical measurement rate where the structure of quantum information changes sharply. This is called a measurement-induced entanglement phase transition. It is not a conventional phase like ice, liquid water, or magnetized iron, because the atoms do not necessarily develop a new visible arrangement. It is a dynamical phase of quantum information, defined by how entanglement, memory, and recoverable information are organized across a continuously monitored many-body system. The individual measurement outcomes are random, but when researchers examine many complete measurement records, stable large-scale patterns emerge, much as countless unpredictable molecular collisions can collectively produce a precise temperature or pressure. Experiments have now observed signatures of these regimes on both trapped ion and superconducting quantum processes. A trapped ion study found evidence for a purification transition between a phase that quickly loses uncertainty under measurement and a coding-like phase that protects part of its initial information for long periods. A separate experiment using up to 14 superconducting qubits observed the expected change between extensive and sub-extensive entanglement scaling as the measurement rate was varied, together with finite-size signs of critical behavior. Larger superconducting processor experiments have also detected finite-size manifestations of measurement-induced information phases and measurement-enabled teleportation across systems containing as many as 70 qubits. Measurement is therefore not merely a passive act that reveals a state already waiting to be found. Repetition can become a physical influence that competes with interaction, protects some information, destroys other information, and reorganizes the system into a new collective regime. Yet the transition cannot be understood by watching one measurement alone. It appears only when you step back and examine how thousands of small observations reshape the architecture of the whole. The deeper lesson is almost paradoxical. Looking at a system can destroy its quantum connections, but looking at it at the right rate can also create a new form of order, one made not from where particles sit, but from which secrets the many-body state can still keep. Quantum memory can reverse the apparent direction of heat flow. A colder quantum object can transfer energy into a hotter one, making the temperature difference grow instead of fade. And the reason is not a hidden refrigerator, but information stored in the relationship between them. Under ordinary conditions, heat flows from hot objects toward cold ones because the combined system can reach vastly more disordered arrangements that way. Place a warm cup beside a cool room, and energy spreads outward until their temperatures approach equilibrium. But this familiar rule quietly assumes that the two objects begin without useful knowledge about one another. Quantum systems can violate that assumption. Two particles may carry correlations established before they are brought into thermal contact, meaning the state of one contains information about the state of the other, even though each particle, examined alone, appears to have an ordinary temperature. That shared information functions like a memory of their joint preparation. In a nuclear magnetic resonance experiment, researchers used two nuclear spins inside a molecule, prepared each spin with its own effective temperature, and then allowed them to exchange energy through a controlled interaction. When the spins began without correlations, energy behaved normally and traveled from the hotter spin toward the colder one. When specially designed quantum correlations were added, the initial flow reversed. Energy left the colder spin and entered the hotter one for a limited period. Viewed only through the local temperatures, the result looked as though the arrow of heat had turned backward. Yet the complete accounting showed that no thermodynamic law had been broken. As the unusual heat flow continued, the correlations between the spins weakened. The apparent reversal was purchased by consuming information that had been stored in their shared quantum state. Once that resource was depleted, the ordinary direction of heat flow returned. The experiment, therefore, did not create free energy, reduce total disorder without cost, or offer a machine that could cool one object forever while heating another. It revealed that temperature alone does not contain the full thermodynamic story when systems begin with memory of each other. The second law remains valid, but its most familiar form must be expanded to include changes in correlation and information. A simple analogy is two sealed envelopes containing instructions that make no sense separately. Each envelope looks random when opened alone, but together they reveal an organized message capable of guiding an action. The useful order was never visible inside either envelope by itself. It existed between them. Quantum correlations can store thermodynamic order in a similar way. When that order is released, it can temporarily push energy against the direction predicted from temperature alone. This result changes the way you might think about heat. It is not merely a substance sliding down a temperature slope. Its direction also depends on what the interacting systems already know about one another through their physical correlations. In large everyday objects, such delicate memories are rapidly scattered into the environment. So the old rule remains overwhelmingly reliable. At the quantum scale, however, information can become a fuel hidden between particles, briefly making cold feed hot while the deeper balance remains intact. The arrow of heat was not destroyed. Part of what guided it had been stored somewhere you were not accustomed to looking, not inside either object, but in the quiet memory they shared. A chaotic quantum system can contain rare states that refuse to become chaotic. Hidden inside a quantum system that forgets almost everything can be a tiny family of states that continues to remember exactly how it began. Most isolated systems containing many interacting particles are expected to thermalize. Even without touching an outside heat bath, their internal interactions spread energy and information among countless possible arrangements until small parts of the system become almost indistinguishable from parts of an object at equilibrium. Begin with atoms in a recognizable pattern. Wait long enough, and that pattern should dissolve into complicated correlations that no simple local measurement can reconstruct. This tendency is one expression of quantum chaos, and it explains why everyday matter reaches stable temperatures instead of endlessly replaying its microscopic past. Yet experiments with chains of highly excited Rydberg atoms uncovered a striking exception. Researchers arranged as many as 51 atoms in a line and prepared them in an alternating pattern, with every other atom excited. The atoms were governed by a strong blockade effect. Exciting one atom made it difficult for its nearest neighbors to become excited at the same time. After the interactions were suddenly activated, The initial pattern began to disappear as expected, but then part of it returned. The atoms repeatedly moved away from the starting arrangement and later revived near it, producing surprisingly persistent oscillations instead of quickly settling into featureless equilibrium. The system was not integrable, carefully separated into independent pieces or protected by random disorder. Most of its possible states still behaved chaotically. The explanation emerged when theorists examined the system's energy states and found a rare sequence now known as quantum many-body scars. These unusual states are embedded among an enormous number of ordinary thermal states, yet they have distinctive structures, unusually low entanglement compared with neighboring states of similar energy, and strong connections to particular simple atomic patterns. The alternating state used in the experiment overlapped heavily with this special family. Rather than spreading equally across the full chaotic spectrum, its evolution repeatedly traveled through the scarred subspace, allowing the recognizable pattern to partially reconstruct itself. The word scar comes from earlier studies of single quantum particles moving through chaotic enclosures, where some wave patterns remain concentrated near unstable repeating trajectories instead of spreading uniformly. Many-body scars extend the idea into systems containing numerous interacting particles, although the detailed mechanism is richer and remains an active field of study. They do not make the whole system immune to thermalization. Most initial arrangements still lose their identity rapidly, and experimental imperfections eventually weaken the revivals. Changing the interactions in the wrong way can destroy the scar structure and restore ordinary thermal behavior. The exception is therefore highly selective. The system remembers certain beginnings while forgetting almost all others. This makes scars valuable not only as a challenge to statistical physics, but as a possible route toward preserving controlled quantum motion inside systems that would normally scramble information. Their existence shows that chaos does not always erase structure evenly. A vast spectrum can look thermal almost everywhere and still contain rare pathways through which coherence survives far longer than expected. You might imagine a crowded city in which nearly every traveler becomes lost in the shifting streets, while a few routes repeatedly return to the same quiet square. The square does not stop the city from being chaotic, and most travelers never find it. But its presence proves that forgetting is not absolute. Deep inside a system built to dissolve its past, nature can preserve a narrow set of memories, not by freezing them, but by allowing them to move through chaos and somehow find their way home. The arrow of time may emerge from information that becomes impossible to recover. Break a drop of ink apart inside a glass of water, and the laws governing every molecule still allow the motion to run backward. Yet no hand could realistically collect the scattered color and rebuild the original drop. This contrast lies at the heart of the arrow of time. At the microscopic level, the equations describing an isolated quantum system generally preserve information and permit reversible evolution. If you knew the complete state with impossible precision and could reverse every interaction without error, the system could in principle return toward its beginning. But real observers never possess that complete description. As particles interact, information about a simple initial state spreads into increasingly complicated correlations among many degrees of freedom. A local disturbance that was once easy to identify becomes encoded in the joint condition of the entire system, like one word dispersed across millions of shuffled letters. This process is called scrambling. The information has not necessarily been destroyed, but retrieving it would require control over an enormous number of particles. Knowledge of their correlations and a reversal performed with extraordinary accuracy. Experiments on quantum processes have verified scrambling by showing that initially, local quantum information can become distributed non-locally across a system while remaining recoverable only through a carefully designed global protocol. From the limited viewpoint available to you, the information is effectively gone. You stop tracking microscopic phases, environmental vibrations, escaping photons, and all the tiny correlations created along the way. This deliberate loss of detail is known as coarse graining. And once those inaccessible variables are ignored, many different microscopic arrangements become indistinguishable. Entropy rises because the number of hidden arrangements compatible with the visible state has increased. A shattered cup appears irreversible not because its atoms have forgotten physics, but because the information required to coordinate their return has escaped into air currents, sound waves, heat, light, and microscopic motion throughout the room. Even a nearly isolated quantum system can display measurable irreversibility when a forward process becomes statistically distinguishable from its time-reversed version. And experiments with controlled spins have linked this asymmetry directly to entropy production. The distinction between impossible and practically unrecoverable is crucial. Quantum mechanics does not generally declare that the past has been erased from existence. Instead, the past becomes encoded in a form so widely distributed and so sensitive to disturbance that no realistic observer can reconstruct it. A single missing detail can prevent an attempted reversal from retracing the original evolution, and the error itself may spread until the returning state bears almost no resemblance to the beginning. This is why the future feels open while the past feels fixed. The present contains abundant records of earlier events, memories, photographs, fossils, heat, and environmental traces. But it contains no comparable records of events that have not happened. Producing those records spreads information outward, and the spreading gives time its practical direction. The universe may therefore possess reversible laws while creating an irreversible world for creatures who can access only fragments of its total state. You experience time as something that carries moments away, but perhaps nothing is truly being carried. Perhaps each moment is being hidden inside correlations too vast to unfold, and what you call the passage of time is the growing distance between information that still exists and information you could ever hope to recover. Particles' superposition may exist only relative to the object observing it. The particle that appears to occupy two places at once from your laboratory may occupy one perfectly definite place relative to another quantum object traveling beside it. This does not remove superposition from quantum physics. It reveals that a superposition must always be defined relative to something. Position is never an isolated label written onto an object. It describes a relationship between the object and a reference system, a laboratory, a measuring device, another particle, or any physical body capable of defining an origin. Imagine that two particles are prepared so that they always remain a fixed distance apart, but their pair has no definite location relative to the laboratory. From your laboratory's perspective, the first particle may be in a coherent combination of two positions, with the second particle shifted alongside it in each alternative. You describe both particles as spatially spread and strongly correlated. Now adopt the first particle itself as the reference frame. Relative to that particle, it is not floating between two locations. It defines the origin and therefore occupies one definite relational position. Because the distance between the particles was fixed in every branch, the second particle can also appear at one definite location relative to the first. The spatial superposition has not been annihilated. It has moved into the description of the laboratory, which now appears in a combination of positions relative to the particle. Quantum reference frame theory provides formal transformations for changing between these descriptions and shows that superposition is a frame-dependent feature. While all correctly translated, experimental probabilities remain consistent. This is more than the familiar statement that a moving passenger sees the station moving backward. A classical passenger and station each follow one definite trajectory, so changing frames merely changes their numerical coordinates. A quantum reference system can itself occupy several coherent positions, velocities, or orientations relative to another system. Changing into its frame must therefore transform several coordinate relationships at once, redistributing uncertainty across the complete description. A particle that looks delocalized relative to a large apparatus may look localized relative to a nearby quantum companion, while the apparatus inherits the delocalization. The word observer here does not mean a conscious mind whose attention creates reality. It means a physical reference system against which measurements are defined. An atom can serve as such a frame, and no human needs to know the result for the relational description to matter. This also explains why asking whether a particle is really in superposition can be incomplete. You must ask, superposed relative to which clock, ruler, laboratory, or physical object? The answer can change without producing contradictions, because different observers measure different relational quantities. When they later compare records and correctly translate their observables, their predictions agree. Recent work continues to refine how complete quantum systems and their internal subsystems should be represented when the reference frame is itself quantum, underscoring that no external, perfectly classical viewpoint should automatically be treated as fundamental. In everyday life, the Earth, the walls, and your measuring instruments are so massive and so strongly connected to the environment that they provide an extraordinarily stable shared frame. Superposition then appears to belong only to the tiny object being studied. But this stability is practical, not absolute. The laboratory is also made of quantum matter. It merely hides its own uncertainty across an immense environment. At the deepest level, the particle may not carry being in two places as a private property. The superposition may exist in the relationship between the particle and the object from which it is observed. Change that physical relationship, and the uncertainty does not disappear into nothing. It quietly changes ownership, leaving you with a universe in which no object tells the whole spatial story alone. An event may have no absolute location until a reference system is chosen. A flash of light can occur unmistakably, leave a detector record, and still have no absolute answer to the question of where it happened. Even in ordinary relativity, a location is never meaningful by itself. It must be specified relative to rulers, clocks, landmarks, or physical fields. Different coordinate systems can assign different numbers to the same event without disagreeing about anything observable, because what remains real is the coincidence. The flash met the detector, two world lines crossed, or a clock displayed a particular reading when an interaction occurred. Quantum physics makes this relational idea far stranger, when the reference systems and even the geometry used to locate events are allowed to exist in superposition. Imagine a massive object arranged in two possible configurations, each producing a slightly different gravitational environment. A nearby interaction may be sharply localized within each configuration, yet comparing its location across the two branches requires you to decide which physical features count as the same landmarks in both. You might use the massive object itself, a collection of clocks or fields spread through the region, to build that comparison. Change those reference systems, and an event described as occurring at the same place in both branches can instead appear at different places, while an event that looked spatially delocalized can become localized. Recent work on quantum coordinates has shown that the identification of locations across superposed geometries depends on the quantum reference frame used to connect them. Consequently, an event's space-time location should not always be treated as an intrinsic label that exists independently of that choice. This does not mean a laboratory accident can be moved by describing it differently, nor that physical consequences become optional. Every frame must preserve relational observations such as which systems interacted, what the instruments recorded, and whether interference can later be observed. The uncertainty concerns how one maps the event from one branch of the quantum description onto another. General relativity already warns that bare coordinates possess no physical identity. An empty point called here has meaning only through what occupies it, and how it relates to surrounding matter. The quantum version deepens the warning, because the matter used as your map may itself lack one classical configuration. Researchers studying quantum clocks have similarly found that the temporal localization of an operation can depend on which physical clock is chosen, especially when quantum systems influence the gravitational relationships between the clocks. An event can therefore be definite relative to one operational frame, while spread across several possible locations relative to another, without allowing either observer to invent arbitrary outcomes. This remains a developing theoretical framework, rather than proof that macroscopic spacetime routinely loses all localization, but it exposes an assumption so familiar that you rarely notice it. You imagine events occurring inside a pre-existing container called space, each one stamped with an address before anything observes it. Quantum reference frames suggest the address may emerge only when the event is related to physical markers capable of defining one. The flash is real, the interaction is real, and the record may be permanent, yet the place assigned to it may not belong to the event alone. Perhaps the universe contains occurrences and relationships first, while locations are the quiet maps constructed when one part of reality is chosen to describe another. Two particles may exchange properties without exchanging their bodies. Two atoms can remain in their own traps while the quantum identities written inside them trade places. Picture one atom holding an internal state that represents 0 and another holding a state that represents 1. Their nuclei do not need to cross the laboratory, and the atoms do not have to exchange positions. When an appropriate interaction is switched on between them, the combined quantum state evolves so that the excitation associated with the second atom begins to appear in the first. Halfway through the process, neither atom possesses a complete independent answer. The two possibilities can form an entangled state in which the excitation is shared across the pair. If the interaction continues for the correct duration, the transfer becomes complete. The first atom now carries the state that originally belonged to the second, and the second carries the state that began in the first. Quantum computing calls the ideal version of this transformation a swap gate. What has moved is not the material body of either atom, but the information encoded in properties such as spin, polarization, or an electronic excitation. Experiments with neutral rubidium atoms confined in optical lattice double wells have observed repeated interchange of spin states through controlled exchange interactions, demonstrating the key physical mechanism needed for a neutral atom swap operation. The word exchange can be misleading because no detachable package of spin flies visibly through the space between the atoms. The transfer emerges from their joint evolution. During the interaction, it may no longer be meaningful to say that the changing property belongs exclusively to either particle. The pair temporarily behaves as one connected quantum system whose state cannot be reconstructed from two separate local descriptions. Energy and angular momentum are still conserved, and some real interaction must mediate the transformation. It is not instantaneous communication, the creation of a duplicate, or teleportation without a physical channel. In fact, the no-cloning principle prevents an unknown quantum state from simply being copied while the original remains untouched. A true swap preserves this rule by transferring the states in both directions. Each system gives up what it originally carried as it receives the state of the other. Related experiments have even swapped a quantum state between very different physical carriers, such as a photon and a single atom, showing that the information defining a qubit can move between systems without requiring the material carriers themselves to become one another. This ability is essential for quantum technology because different objects are useful for different tasks. Photons can transport information over distance, atoms can store it, and superconducting circuits can process it rapidly. A controlled exchange lets the information move to whichever body can protect or manipulate it best. Yet the idea also reveals something deeper about what you call a property. In ordinary life, a color seems attached to a surface, and a memory seems attached to a particular brain. At the quantum level, an internal state can be transferred so completely that the receiving particle reproduces every prediction associated with the original state, while the bodies remain where they were. The atoms keep their places, masses, and physical continuity, but the informational pattern by which you distinguish them has changed owners. For a moment, nature separates the enduring carrier from the state it carries, quietly suggesting that an object may be less defined by the matter occupying its location than by the changeable information temporarily entrusted to it. A photon's wave-like nature can be separated from its particle-like nature. A single photon can enter one optical device and leave behind evidence suggesting that its wave-like behavior occupied one route, while its particle-like behavior occupied another. Light normally reveals its wave aspect through interference, where several possible paths combine to create bright and dark patterns, while its particle aspect appears through localized detector clicks and path-distinguishable behavior. These qualities are complementary. The more clearly an experiment reveals which route a photon took, the less sharply it usually displays interference. Yet researchers have constructed a carefully controlled experiment inspired by the quantum Cheshire cat in which wave-like and particle-like states were first encoded, within different combinations of the photon's path and polarization, then sent through an interferometer and examined using weak disturbances. The photon was prepared in a coherent mixture of a state designed to respond like a wave and another designed to respond like a particle. After this preparation, the experimenters selected only photons satisfying a particular final condition and measured how tiny disturbances placed in each path altered the probability of successful detection. The extracted weak values produced a striking division. The response associated with the wave-like state was concentrated in one arm, while the response associated with the particle-like state was concentrated in the other. In this operational sense, the two expressions of the same photon were spatially separated. The claim must be understood carefully. The experiment did not tear a photon into a physical wave fragment and a miniature particle fragment, nor did it prove that a photon carries two detachable substances. Wave and particle here refer to deliberately encoded quantum states defined by the kinds of interference behavior they can produce. And the separation was inferred statistically from weak measurements performed across many prepared and post-selected photons. No individual detector photographed a wave traveling alone through one corridor while a tiny pellet crossed the other. The observed pattern emerged from the complete preparation, interference, disturbance, and final selection procedure. Even so, the result challenges the simple picture that wave-like and particle-like behavior must always remain attached to one indivisible route. Complementarity was not violated because the experiment did not obtain unrestricted, perfectly sharp witch-path information and full interference visibility from the same ordinary measurement. Instead, it arranged the quantum information so that different weak responses appeared in different regions, while the complete state remained coherent. The photon still arrived as one localized detection event, yet the evidence leading to that click could not be described as one classical object carrying all its familiar attributes along one path. You may imagine wave and particle as two masks that light alternates between depending on how you look, but this experiment suggests something more subtle. Under carefully chosen conditions, the masks can leave their signatures in different places, even though only one photon enters and one photon is finally detected. What appears indivisible in the finished event may have been distributed throughout the experiment, reminding you that quantum properties are often not private possessions carried by objects, but patterns revealed by the relationships between preparation, possible paths, and the questions used to examine them. The space of all possible states can break into regions that cannot reach one another. Imagine an enormous palace containing every arrangement a quantum system could possibly take, only to discover that most of its doors are painted onto the walls, and entire wings can never be reached from one another. Physicists call this abstract palace Hilbert space, not a physical location, but the complete collection of states available to a system. For a chain or lattice containing many particles, this space becomes unimaginably large because every different distribution, orientation, and internal configuration corresponds to another possible state. You might expect that if the particles interact for long enough, the system could gradually explore all states compatible with obvious conserved quantities, such as total energy or particle number. In certain constrained systems, however, the permitted microscopic moves divide this space into many dynamically disconnected regions known as Krylov sectors. A state beginning in one sector can evolve through every doorway allowed inside that region, but can never cross into another sector, even when states on the opposite side possess the same total energy and the same number of particles. The barrier is not a high wall of potential energy. It is a rule embedded in the dynamics. A particle may be allowed to move only when a neighboring pattern changes with it. Pairs may hop while isolated particles cannot. Or the system may conserve not only the amount of a quantity, but also how that quantity is distributed across space. Each local restriction seems modest, yet together they can divide the full state space into an exponentially growing number of isolated pieces. This phenomenon is called Hilbert space fragmentation. It differs from an ordinary symmetry that separates states into a small number of broad categories. Fragmentation can split even one conventional symmetry sector into a vast collection of smaller regions, some containing many active configurations and others consisting of frozen states with no permitted move at all. The consequence is a powerful dependence on the beginning. Two systems can contain the same energy and particle number, obey the same physical laws, and still relax in radically different ways because their initial states belong to disconnected sectors. One may spread and rearrange extensively, while the other remains trapped near its original pattern, not because it lacks energy, but because no legal sequence of local operations leads outward. In 2024, an experiment using ultra-cold atoms in a two-dimensional tilted optical lattice observed this kind of fragmentation directly. Researchers prepared different atomic patterns with comparable global properties and found sharply different relaxation behavior. They also created defects whose motion was restricted to lines or nearly frozen points, manifestations of fracton-like dynamics produced by the same constraints. The experiment showed that the disconnection is not merely a mathematical curiosity. It can determine where real atoms travel and which patterns they can ever become. This does not mean that every fragmented boundary is eternally indestructible. Additional interactions, experimental imperfections, or processes that violate the constraint can open weak passages between sectors, allowing slow leakage and eventual relaxation. But when the rules are sufficiently accurate, the system behaves as though its possibilities have been divided into separate worlds that share one laboratory yet cannot communicate through the available dynamics. You usually think that knowing all possible states tells you what a system might eventually do. Fragmentation reveals that possibility is not enough. A destination may exist, possess the correct energy, and sit inside the same mathematical universe, yet remain unreachable because nature provides no sequence of allowed steps leading there. The future is shaped not only by which states exist, but by which invisible doors the laws of motion have chosen to make real. Some quantum states remember their beginning, while everything around them forgets. At the edge of a quantum chain, a single spin can continue behaving as though the experiment has only just begun, even after the crowded interior has scrambled nearly every visible trace of its past. Ordinarily, interacting particles share energy and information until simple starting patterns disappear into complicated many-body motion. A spin initially pointing upward becomes entangled with its neighbors. Those neighbors influence particles farther away, and before long, no small part of the system preserves a readable copy of the beginning. Yet certain one-dimensional quantum systems contain an unusual structure called a strong zero mode, a collective operator concentrated near the boundary that is almost unchanged by the system's evolution. Although its influence is strongest on the first few particles, it is not merely one isolated edge spin protected behind a wall. It is a carefully organized pattern extending into the chain with progressively weaker contributions, constructed so that the effects trying to disturb it nearly cancel. Because of this hidden structure, information encoded at the boundary can remain coherent for an extraordinarily long time, even while excitations move through the interior and the bulk approaches thermal-looking behavior. In exactly solvable models, An ideal strong zero mode can preserve boundary memory indefinitely, including at extremely high effective temperatures where almost every energy state participates. In less perfect systems, an almost strong zero mode can still produce a long plateau during which the edge remembers its original orientation before weak imperfections eventually cause decay. The survival time can grow extremely rapidly as the system is tuned deeper into the protected regime. So a modest change in the interactions may produce a dramatic increase in memory. This is different from the rare scarred states discussed earlier. Quantum scars preserve special motion because particular initial states overlap with exceptional energy states inside an otherwise chaotic spectrum. Strong zero modes instead protect information associated with a boundary across a broad range of energies, pairing states throughout much of the spectrum and preventing the edge degree of freedom from easily surrendering its identity to the bulk. Recent experiments on a large superconducting quantum processor have observed long-lived topological edge coherence in a disorder-free, finite temperature setting by engineering pre-thermal strong zero modes whose coupling to mobile bulk excitations was strongly suppressed. The researchers used these edge modes as logical quantum bits and maintained coherent correlations, while the surrounding system remained active rather than frozen. The protection is not magical and it is not eternal in a realistic machine. Noise, imperfect controls, unwanted interactions, and sufficiently long observation times can eventually allow the boundary information to leak away. Still, the phenomenon shows that thermalization need not erase every part of a quantum object at the same rate. A system can lose the details of its interior while sheltering one carefully encoded fragment at its edge, almost like a building whose rooms forget every conversation, while a faint inscription near the doorway remains untouched. The beginning has not survived everywhere. It has found one narrow place where the dynamics struggle to reach it, reminding you that forgetting is not always a uniform collapse into disorder. Sometimes it is a tide that covers the entire landscape while leaving one small boundary above the water. A measurement can produce a value far beyond any value the system normally has. A quantum spin that can normally answer only up or down can make a measuring device respond as though the answer were 100, but only when the question is asked so gently that no ordinary result is obtained. In a standard strong measurement, the apparatus forces a system into one of the allowed outcomes, so a two-valued spin measurement never reports an arbitrarily large physical spin. A weak measurement works differently. The system is coupled only faintly to a pointer, allowing each trial to disturb it very little. But the pointer shift from a single ordinary experiment is then too small and noisy to reveal much. The strange result appears when researchers prepare the system in one state, interact with it weakly, and afterward keep only the trials in which a second measurement finds a carefully chosen final state. This final filtering is called post-selection, when the initial and final states are nearly incompatible. The surviving trials are rare, but the tiny contributions associated with different quantum alternatives can interfere so that the average pointer shift of the selected group becomes much larger than the normal range of the measured observable. The resulting quantity is called an anomalous weak value, a Aharonov-Albert, and Vaidman introduced the idea in 1988 with the deliberately shocking example of a spin component producing a weak value of 100 even though an ordinary measurement could never return that value. The essential warning is that the particle has not secretly acquired 100 units of spin. A weak value is not an ordinary eigenvalue revealed with greater precision, and it should not be interpreted as a strong measurement result that existed inside the system all along. It describes the conditional response of a weakly coupled measuring device when both the preparation and the later selection are taken into account. The enormous shift is balanced by the small probability of obtaining the required final result, so the procedure does not create unlimited energy, information, or measurement sensitivity for free. When all trials are included, rather than only the rare selected ones, the overall statistics remain consistent with standard quantum mechanics. Experiments have repeatedly observed anomalous weak values, including a 2021 single photon demonstration in which the measured weak value lay far outside the observable's normal spectrum, and the uncertainty was smaller than the distance to the nearest allowed ordinary value. Under appropriate experimental assumptions, anomalous weak values are also connected to quantum contextuality. They cannot always be explained by imagining that the system carried a fixed, measurement-independent value before the apparatus interacted with it. Their practical use is equally subtle, because a small physical change can produce an amplified pointer displacement in the selected data. Weak value methods can help detect tiny shifts when technical limitations dominate, although post-selection also discards many events and does not automatically improve the total fundamental precision. What appears at first to be an impossible number is therefore not a broken measuring scale. It is a sign that quantum measurement cannot always be understood as opening a box and reading a property stored inside. The value can belong to the entire passage from preparation through a gentle interaction to a rare final condition. And when that passage is arranged with extraordinary care, the pointer may travel far beyond the territory the system could ever occupy in an ordinary measurement, showing you that the answer to a quantum question may depend as much on how the question ends as on how it began. Cause and effect may be properties that emerge only at large scales. Run a perfect film of two interacting quantum systems backward, and the microscopic equations may remain valid, even though your entire understanding of cause and effect has been reversed. A collision can be calculated from an earlier state toward a later one, but the same underlying dynamics can often be used to reconstruct the earlier state from the later one. The mathematics connects events without necessarily stamping one event with the word cause and the other with the word effect. In science, causation usually means more than sequence or correlation. To say that A caused B, you imagine changing A while leaving the relevant background unchanged, then asking whether B would respond. This works beautifully with large, stable objects. You can press one switch without rebuilding the entire electrical grid, remove one domino without altering every molecule in the room, or vary a medicine while comparing groups whose other conditions are controlled. At the quantum scale, however, the separation required for such interventions can become difficult to define. A system may already share correlations with its surroundings, and altering one part can change the physical context used to describe the others. A measured correlation might have arisen from direct influence, a shared source, or a more complex quantum relationship, so the data alone may not immediately reveal which event should be called the cause. Quantum causal inference research has developed ways to distinguish some of these possibilities, and photonic experiments have demonstrated algorithms that identify whether observed 2-qubit correlations arose from a direct causal influence or from a common cause under specific controlled assumptions. Yet this does not prove that causality is absent from fundamental physics. Some theories build causal structure deeply into space-time or quantum fields, while other approaches suggest that the familiar causal arrow becomes clear only after many microscopic interactions have formed a stable macroscopic world. At large scales, environmental decoherence suppresses delicate alternatives. Records are copied into many surrounding systems, and certain variables become robust enough to manipulate without controlling every atom involved. These stable variables allow you to speak meaningfully about interventions. Changing the pressure moves the piston, opening the valve releases the gas, and striking the match ignites the fuel. The direction also becomes asymmetric, because the universe presents highly organized earlier conditions and increasingly complex later correlations. Theoretical work has argued that the typical growth of entanglement and complexity can help distinguish the simpler direction from which a quantum process began from the vastly more intricate direction into which it evolved, providing a possible physical foundation for causal asymmetry even when the fundamental dynamics does not privilege past over future. On this view, cause and effect resemble temperature. No individual molecule possesses a temperature by itself, yet immense collections of molecules produce a quantity so reliable that engines, climates, and living bodies depend on it. Causation may likewise emerge when countless quantum relationships settle into patterns stable enough to be controlled, remembered, and used for prediction. The spark still causes the flame in every practical sense, but perhaps the universe did not begin with a tiny invisible arrow pointing from one to the other. Perhaps that arrow appeared only when reality became large enough to preserve records, support interventions, and turn an underlying web of reversible relationships into the one-way stories through which you understand the world. Quantum correlations may function like a hidden thermodynamic fuel. Two quantum systems can each look completely exhausted when examined alone, yet together they may still contain enough organized information to raise a weight. Imagine two small systems whose individual states are thermal, meaning that neither one offers extractable work through an ideal cyclic operation performed locally. Their energy populations are already arranged in the passive order expected at equilibrium, so each system resembles a battery whose accessible charge has been drained. But now examine the pair as one object. The systems may be correlated so that knowing the condition of one reveals something about the other, and those joint patterns can create an imbalance invisible in either subsystem separately. A global operation that accesses both systems can convert part of this hidden order into useful work, lowering the pair's energy while charging an external storage device. The energy was not created by observation, and the correlations were not a mysterious force added from outside. Instead, the joint state contained less uncertainty and more exploitable structure than its local appearances revealed. Researchers have shown that the extractable work of correlated quantum ensembles can be separated into local contributions and a global contribution stored specifically in correlations. Even when every component is locally thermal, work may remain available from the collective state. Entanglement can enhance this resource for small collections, but entanglement is not always required. Classical correlations can also store useful order, while genuinely quantum correlations become important when they enable advantages that no comparable classical strategy can reproduce. In feedback-based protocols, measuring one part can reveal which operation should be applied to the other, increasing the amount of work that can be extracted. The improvement has been linked to quantum discord and, for pure states, to entanglement, showing that correlations can acquire a direct operational value rather than serving only as abstract evidence of quantum strangeness. More recent theoretical work has identified tasks in which steerable quantum correlations, strong correlations that allow one party's choice of measurement to prepare distinct ensembles for another, provide a work extraction advantage beyond all unsteerable strategies, with the potential advantage increasing as the system's dimension grows. None of this permits an engine to run forever. As work is extracted, the useful correlations are weakened, rearranged, or consumed. Restoring the original correlated state requires physical resources, and any memory used to guide feedback must eventually be reset if the cycle is to repeat. The second law survives because the complete balance includes the preparation, measurement, communication, and erasure costs rather than counting only the energy gained at the final step. What changes is your understanding of where thermodynamic value can hide. You are accustomed to searching inside objects for fuel, in chemical bonds, elevated weights, compressed gases, or excited atoms. Quantum thermodynamics asks you to search between objects as well. Two systems may reveal nothing useful when opened separately, while their relationship still contains an ordered pattern capable of performing work. The fuel is not located in either body alone. It lives in the agreement between them, waiting for an operation that knows how to read a resource written across the space where individual descriptions end. A quantum battery may charge faster because its parts act collectively. A row of quantum battery cells can absorb energy faster when they are charged as one coordinated object than when the same cells are filled independently, even though the final amount of stored energy may be identical. To see the difference, Imagine 12 small two-level systems, each able to occupy a low-energy or high-energy state. In a parallel protocol, 12 separate charging interactions act on the cells one by one, so adding more cells increases both the battery's capacity and the total charging power in the ordinary linear way. A collective protocol connects the cells through a shared charging process, allowing transitions in one part of the battery to participate in the evolution of the others. The system then moves through its joint state space, rather than following 12 unrelated charging paths, and the time required to reach a highly energized state can decrease as the battery grows. This is called a collective quantum charging advantage. The advantage concerns power, energy deposited per unit time, not the creation of extra energy, and it must be tested under fair limits on the strength and resources of the charging interaction. Early theoretical work showed that collective operations can enhance charging power and established bounds on how the advantage depends on how many cells may interact at once. Importantly, entanglement can accompany the process, but is not always the sole cause of the speed-up. Later analysis found that the strongest possible scaling requires genuinely global control over the battery, and that the total power can grow at most quadratically with the number of cells when comparable physical resources are used, rather than increasing without limit. This distinction matters because an apparently spectacular speed-up can be manufactured simply by applying a stronger charger to the larger battery. A real quantum advantage must survive after the available energy scale, interaction strength, and number of uses are properly accounted for. The idea has now moved beyond ideal equations. In a 2026 experiment, researchers implemented collective charging in chains containing between 2 and 12 superconducting transmon qubits, using only nearest neighbor, pairwise interactions, rather than an unrealistic operation, coupling every cell directly to every other cell. They observed a scalable charging advantage over an uncorrelated comparison protocol and measured quantum features including coherence, useful stored energy, and entanglement during the process. These devices are not replacements for lithium-ion batteries. They store tiny amounts of energy, require highly controlled hardware, and can lose their advantage through noise, imperfect timing, leakage, or the cost of preparing the charger. The stored energy must also be extractable in a useful form. Reaching a highly excited state quickly does not automatically guarantee that the battery will release all of it efficiently. Still, the experiment reveals a new principle of energy transfer. Classical intuition tells you that charging more cells should resemble filling more cups. Each cup needs its own stream, and the work grows with their number. Quantum dynamics can instead make the cells respond collectively, more like one instrument whose strings accelerate one another's motion through their shared pattern. No cell secretly receives energy from the future, and no law of thermodynamics is bypassed. The path through which the battery absorbs energy has simply become cooperative. Perhaps that is the deeper lesson hidden inside the device. Sometimes speed does not come from pushing every part harder, but from arranging the parts so carefully that they no longer have to move toward the destination alone. Measurement alone can push quantum matter through a phase transition. Remove every ordinary driving gate from a quantum circuit, leave only a sequence of measurements, and the system can still cross from one collective phase into another. This seems impossible if you think measurement merely reads what is already there. A projective measurement is itself a physical operation. It changes the state by selecting an outcome and reorganizing the correlations compatible with that outcome. A measurement involving several qubits can even create entanglement between them, because it may reveal a shared property without determining the individual states that produce it. Now imagine a chain of quantum spins repeatedly subjected to two incompatible kinds of measurement. One kind examines a property of neighboring spins together and tends to bind information across the links of the chain. The other examines individual spins in a different basis and tends to localize information around separate sites. Because the two questions do not commute, answering one disturbs the structure established by the other. If the first measurement is chosen more frequently, the long-time state develops one pattern of correlations. If the second dominates, a different pattern appears. At a critical balance, the way entanglement stretches through the chain changes sharply, producing a measurement-driven phase transition, even though no Hamiltonian evolution or unitary gate is present. The projective transverse field Ising model provides a clear theoretical example. It contains two competing non-commuting projective measurements and no unitary dynamics. Yet numerical work finds a transition between two distinct steady-state entanglement phases, with critical behavior connected to percolation. More general measurement-only circuits can support symmetry breaking, symmetry-protected topological, critical, and highly entangled phases depending on which collective properties are measured and how often each measurement is applied. These results are primarily theoretical and numerical, rather than proof that an ordinary solid can be transformed into a new visible material merely by watching it. The word measurement also does not mean a conscious person repeatedly looking at a screen. It means a controlled interaction that transfers information from the quantum system into an apparatus or record. Each individual outcome is random, so one experimental run can look like a noisy sequence of clicks. The phase becomes apparent only when physicists study how information and entanglement behave across many possible measurement histories. In some models, the ordinary density matrix obtained by averaging over all outcomes hides the transition completely. The distinction survives only in the conditioned quantum trajectories that retain the full measurement record. This makes the phases scientifically unusual, because the order is not always visible in a simple local quantity, such as magnetization or density. It may reside in how difficult it is to separate one region from another, whether information at an edge remains protected, or whether a hidden logical qubit survives the accumulating observations. Measurement can therefore do more than destroy quantum behavior. One set of measurements may cut connections, while another builds non-local constraints that protect or rearrange them. The phase is created by the competition between questions. There is no cooling bath guiding the system toward a lowest energy state, and no conventional force instructing the spins how to align. The repeated extraction of information becomes the dynamics. You begin with the familiar belief that observation comes after reality has chosen its form, like reading a label attached to an object. Measurement-only phases suggest a more active relationship. Ask one kind of question often enough, and quantum matter settles into one architecture of information. Change the questions, and the architecture can reorganize completely. What crosses the critical point is not simply matter in space, but the pattern of what the system is repeatedly forced to reveal, and what, despite all that observation, it is still able to keep hidden. Observing a system more frequently can destroy entanglement across the whole system. There is a point at which watching a quantum system no longer reveals its hidden connections, but prevents those connections from spreading at all. Picture a long chain of qubits beginning in a simple state, while interactions repeatedly pass quantum information from neighbor to neighbor. Left undisturbed, these interactions create entanglement across greater distances, until the condition of a small region can no longer be described independently of the rest of the chain. The system gradually builds an invisible network in which information about the beginning is distributed through collective correlations rather than stored in any single place. Now begin measuring individual qubits at random locations. Each measurement produces a definite local record and removes some of the alternatives that had been participating in the wider quantum state. A single observation may cut only a few threads, and the remaining dynamics can often rebuild them. But as the measurements become more frequent, new connections are broken almost as quickly as the interactions can create them. Eventually, the system enters a quantum Zeno regime in which constant local questioning prevents entanglement from growing across the whole chain. Regions that would otherwise share correlations throughout their entire volume become connected mainly near their boundaries, as though repeated observation has divided one vast fabric into many smaller patches. The name comes from the quantum Zeno effect. where sufficiently frequent measurements can inhibit a system's ordinary evolution. But in a many-particle setting, the effect is not simply one frozen atom. The measurement changes the global architecture of information, limiting how far quantum influence can spread, even while particles continue to evolve locally. Numerical studies of hybrid circuits containing both entangling, operations, and projective measurements find a weakly monitored regime with extensive entanglement, and a strongly monitored Zeno regime in which entanglement remains short-ranged, separated by a continuous dynamical transition. This does not mean that every measurement destroys every form of entanglement. A carefully designed joint measurement can create entanglement, and certain monitored systems can protect special logical information. The outcome depends on what is measured, how often it is measured, and how the measurement competes with the system's own interactions. Nor does observation require a conscious person, a detector, an environment, or any apparatus that records local information can perform the relevant physical measurement. The destructive power comes from information becoming available outside the system, not from a human mind noticing the result. The effect is also visible only when the measurement record is retained and individual quantum trajectories are considered. Averaging blindly over all outcomes can hide much of the structure. What repeated observation removes is not necessarily energy or motion, but the ability of distant parts to remain part of one inseparable quantum description. You may begin with a system whose information is woven across hundreds of qubits, yet sufficiently persistent measurement can force that information back into local pieces. The particles have not stopped existing, and the apparatus has not pushed them apart. The system has simply been asked so many local questions that it can no longer preserve one global secret. Tiny quantum key can unlock far more information than its own size suggests. A more secret key, shorter than a sentence, can determine whether an entire quantum message looks almost meaningless or suddenly becomes readable. In classical encryption, there is a familiar limit. Revealing one additional bit of key should not normally unlock far more than one additional bit of previously inaccessible information, unless the security relies on assumptions about an attacker's computing power. Quantum data locking breaks this intuition by encoding a classical message into quantum states whose useful measurement basis depends on a small secret key. The sender first converts the message into one of many possible quantum code words, then uses the key to choose a transformation that scrambles how those code words appear. An authorized receiver who knows the key can undo the transformation or choose the correct measurement and recover the message with high probability. An unauthorized observer may possess the complete quantum transmission and may even know the entire protocol, yet without the key, no single measurement gives access to much of the encoded classical information. The difficulty is not that the eavesdropper lacks enough particles or has been given a damaged copy. Quantum measurements themselves require a choice, and incompatible choices cannot all be performed perfectly on the same unknown state. A measurement suited to one possible key may erase the distinctions needed for another. The short key, therefore, does not contain the long message in compressed form. It identifies the measurement context in which the information becomes accessible. Early theoretical work demonstrated that a disproportionately small amount of classical communication can unlock a much larger amount of classical correlations stored in quantum states. Later experiments implemented quantum data locking protocols with photons and observed that the amount of information recovered after revealing the key exceeded the size of the key itself, including a demonstration in which an image was transmitted through a lossy quantum channel using locking and error correction. This is not the same as ordinary quantum key distribution. Quantum key distribution creates a shared secret key whose security can be defined strongly enough for use in later cryptographic tasks. Data locking uses quantum encoding to reduce the amount of secret key needed to hide a message, but its security is often expressed through accessible information, the greatest amount an attacker can extract using an immediate measurement. That distinction matters, An adversary with a long-lived quantum memory might store the undercoded states, wait until related information or the key is revealed, and then perform a more useful measurement. Accessible information security is also not automatically composable, meaning a message that appears secure in isolation may not remain equally secure when used inside a larger cryptographic protocol. Researchers have therefore studied locking schemes under conditions such as bounded quantum storage time, where an attacker must measure before the key becomes available. The phenomenon remains extraordinary even with these limits. In the classical world, a locked book contains readable letters hidden behind a physical barrier, and the key merely opens the cover. In quantum data locking, the information can be physically present in the transmitted state, while no measurement available without the key can reveal much of it. The key does not open a container. It tells the receiver which question the quantum message was prepared to answer. Until that question is known, a vast amount of information can remain suspended in plain sight, carried by the system, available in principle, yet inaccessible to anyone who does not know how to look. Quantum information can be hidden from two observers but visible when they reunite. Split a quantum message between two observers, and it is possible to arrange the pieces so that neither observer can learn anything about the original state, even though the complete information remains recoverable when the pieces are examined together. This phenomenon is called quantum masking. Suppose a sender encodes an unknown state into two quantum subsystems and gives one to Alice and the other to Bob. If Alice measures only her subsystem, every possible input produces exactly the same local statistics. Bob encounters the same blank appearance on his side. Neither receives a blurred or incomplete version of the message. Their individual states contain no distinguishing feature that tells them which input was encoded. The information survives only in correlations between their systems, meaning that it becomes visible through comparisons and joint measurements that neither observer can perform alone. This is fundamentally different from encryption with a missing key. In encryption, the data is locally present but deliberately scrambled. In masking, the defining information may be absent from both local descriptions and reside entirely in how the two parts fit together. However, quantum theory places a strict boundary on this ability. The no-masking theorem proves that one fixed physical process cannot mask every possible arbitrary quantum state into two subsystems while preserving all the information only in their correlations. The restriction exists because a general quantum state contains both measurement probabilities and complex phase relationships, and those features cannot all be removed from each local part without losing some of the original state or allowing the local states to change. Restricted families can still be masked. In particular, researchers have shown that the full set of quantum states described using only real amplitudes forms a maximal maskable set. An experiment implemented this idea using a photonic quantum walk, encoding a 4-level real quantum state into 2 qubits, represented by different properties of a single photon. Measurements of either qubit alone revealed no information about the input, while measurements of their correlations reconstructed the hidden state with a reported fidelity of about 99%. A practical network could instead distribute the two subsystems to genuinely separated observers, but they would need to bring their quantum systems together or perform an appropriate coordinated recovery operation to read the protected information. Simply exchanging ordinary measurement results may not be enough if their earlier local measurements have already destroyed the correlations required for reconstruction. The protocol also does not clone the original state. The input is transformed into one shared encoding, and recovering it consumes or changes that distributed form according to the physical operation used. Nor does masking make information disappear from the universe. It moves the information out of the individual parts and into relational properties that exist only at the level of the composite state. This distinction is subtle but important. Alice may inspect every local feature available to her and find nothing. Bob may do the same and reach the same empty conclusion. Only when their systems are reunited does the pattern become readable. as if the message had never belonged to either page, but only to the precise way the pages align. Quantum masking therefore teaches you that information does not always need a local address. It can remain perfectly real, physically preserved, and experimentally recoverable while being located nowhere that either observer can access alone. A quantum state can unlock a power that none of its parts possess alone. 4 distant observers can share a quantum state that appears useless for producing a clean entangled pair. Yet the moment any 2 of them enter the same laboratory, the state can release powerful entanglement between the other 2. The clearest example is the Smolin state, a 4-particle mixed state designed from correlated Bell pairs. Imagine that Alice and Bob share one Bell state, while Charlie and Diana share an identical Bell state. But no one knows which of the 4 possible Bell states was selected. The complete preparation is a balanced mixture over all 4 choices. Because the identity of the Bell state is hidden, the parties cannot ordinarily correct or convert what they hold into a known maximally entangled pair using only separated local operations and classical messages. The state is nevertheless genuinely entangled. It belongs to the unusual class called bound entanglement. Quantum correlation is present, but it cannot be distilled into standard pure entangled pairs under the normal separation restrictions. John Smolin showed that this 4-party state has an extraordinary exception. If any 2 observers physically bring their particles together, they can perform a joint Bell state measurement. That measurement tells them which Bell correlation was shared across the preparation. After they communicate the result, the 2 observers who remained far apart know which correction to apply, leaving them with a known maximally entangled pair that can be used for tasks such as quantum teleportation. The joined observers do not send entanglement across space at the moment of measurement, and no usable message travels faster than light. The remaining pair can exploit the entanglement only after receiving the ordinary classical measurement result. What has changed is access. The useful resource was encoded globally in the 4-party state, but separation prevented anyone from identifying and controlling it. A joint measurement removes the uncertainty that had locked the resource in place. Experiments using 4 photon polarization qubits have prepared Smolin-type states, verified their entangled yet non-distillable character within the tested regime, and demonstrated the unlocking procedure in which a joint operation enables usable entanglement to emerge between the remaining photons. This power does not belong to any single particle, and it cannot be understood by inspecting the particles one at a time. Even looking at one separated pair does not reveal a known Bell resource ready for use. The operational ability belongs to the architecture of the whole state and to the way the parties are allowed to cooperate. Change the grouping of the observers, and a resource that had been bound can become available. Keep everyone isolated and the same state remains locked. This is why multipartite quantum information cannot always be valued by adding up what each component can accomplish separately. The whole may contain a capability that no isolated part displays, not because the parts hide small portions of the same power, but because the power exists only in their collective pattern. The Smolin state leaves you with a quiet reversal of ordinary intuition. Sometimes bringing 2 pieces together does not help those 2 pieces at all. Instead, their reunion opens a door for 2 distant pieces elsewhere, revealing that in quantum physics, the place where an action is performed and the place where its usefulness appears do not always have to be the same. Quantum properties may be less attached to objects than everyday reality suggests. Ask a quantum object the same yes or no question in 2 different compatible measurement arrangements, and you may discover that the answer cannot be explained as a permanent label the object was carrying all along. In everyday life, properties seem securely attached to things. A coin has a particular mass whether it is weighed beside a key or beside a stone, and a red book remains red regardless of which other books share the shelf. This encourages you to imagine a particle as a tiny container filled with hidden answers. One value for every direction of spin. One value for every possible test. all waiting to be uncovered. The Coach-and-Specker theorem shows why that classical picture cannot reproduce quantum mechanics. For certain systems, you can construct groups of compatible measurements that can be performed together without the ordinary excuse that one measurement violently disrupts the next. Each measurement also appears in more than one group, much like the same question appearing in several different questionnaires. If every result were a pre-existing property attached to the object and independent of the other compatible questions asked beside it, you should be able to assign consistent answers to the entire collection. Quantum theory predicts patterns for which no such complete assignment is possible. The contradiction does not mean that logic fails or that the particle deliberately changes its answer when watched. It means that the measurement result cannot always be understood as revealing a private, context-free value that belonged to the object before the experimental arrangement was chosen. Experiments with single photons, neutrons, and trapped ions have observed violations of inequalities that every non-contextual hidden property model must obey. A trapped ion experiment demonstrated this conflict independently of the system's initial state, while photon experiments implemented complete Coach-and-Specker measurement sets using properties such as path, polarization, and orbital angular momentum. These results require careful assumptions about compatible measurements and experimental imperfections. They do not prove that objects possess no properties, that every result is created by consciousness, or that reality changes according to personal belief. Quantum systems still obey precise statistical laws, and repeated experiments produce stable predictions. What contextuality removes is the simplest classical story behind those predictions. A result may belong not to the object in isolation, but to the object as tested within a particular network of compatible questions. This is why contextuality has become more than a philosophical curiosity. It can function as a resource in quantum information processing, where the impossibility of assigning one fixed classical answer sheet can support computational and randomness generating advantages. You normally picture measurement as peeling away a cover to reveal something already written underneath. Quantum contextuality suggests that some answers are more like notes produced by the meeting between the system and the full experimental question. The object is real, the apparatus is real, and the recorded answer is real, but the property may not have existed as a detached possession waiting inside the object. At the smallest scales, reality may be made less from things carrying complete lists of attributes and more from the precise contexts in which those attributes are allowed to become meaningful. System can contain secret correlations that local measurements cannot reveal. 9 perfectly distinguishable quantum states can be placed before 2 observers, with no entanglement inside any of them, and still remain impossible for the observers to identify reliably while they stay apart. This surprising result is known as quantum non-locality without entanglement. Imagine that Alice receives one 3-level particle and Bob receives another. The pair has been prepared in one of 9 mutually orthogonal product states, meaning that every candidate describes Alice's particle and Bob's particle separately, rather than binding them into an entangled state. Because the 9 global states are orthogonal, a suitable joint measurement performed after bringing both particles into one laboratory can distinguish them perfectly. You might expect Alice and Bob to achieve the same result by measuring their own particles, calling one another, comparing answers, and repeating the process as needed. Bennett and his colleagues proved that the specially arranged set prevents this. No sequence of local operations and ordinary classical communication can recover as much information as the appropriate global measurement. The obstacle is not that Alice and Bob see identical blank states, as in quantum masking. Their local systems can reveal partial clues. The problem is that any local measurement strong enough to eliminate some possibilities also risks disturbing the delicate distinctions needed to separate others. The 9 states can be represented as interlocking dominoes across the combined state space. Alice may find a local test that divides one group cleanly, but that same test damages the orthogonality of states that Bob would later need to distinguish. Bob faces the equivalent trap from his side. Classical communication can tell them which tests were performed and which results appeared, but it cannot restore distinctions erased by a poorly placed local measurement. Only an operation that accesses the composite system as a whole can read the complete pattern without breaking it. This is why the phenomenon is called non-local, even though the candidate states themselves are unentangled. It does not violate a Bell inequality, transmit information instantly, or imply that the separated particles exert mysterious forces on one another. The non-locality lies in the measurement required to decode the globally arranged classical information. Later research has constructed even stronger product state sets for several observers, including locally irreducible collections in which no party can begin by safely excluding even one candidate while preserving the distinctions among the rest. The lesson reaches beyond the usual belief that entanglement is the only source of quantum non-local behavior. Sometimes the secret is not hidden inside a mysterious bond within each state. It is hidden in the geometry of the full set of possibilities. Every candidate may be assembled from separate parts, yet identifying which candidate was chosen can demand a measurement that refuses to treat those parts separately. Alice holds one piece, Bob holds another, and each can gather honest information. But the final answer exists only in a question large enough to include them both. Quantum theory therefore draws a quiet distinction between preparing a state locally and understanding it locally. The pieces may never have been entangled, yet the knowledge needed to name the whole can still remain beyond the reach of anyone who insists on looking at the pieces one at a time. Two states with the same energy can contain different amounts of usable work. An energy meter can give exactly the same reading for two quantum states, while one behaves like a charged battery and the other behaves as though it has already been drained. Consider a simple quantum system with a low energy state and a high energy state. In the first preparation, the system is an equal incoherent mixture. Half the time it occupies the lower level and half the time the upper one, with no preserved phase relationship between those alternatives. In the second preparation, it is placed in a pure coherent superposition containing the same 50-50 energy populations. Measure the energy many times, and both preparations produce the same average result. So by ordinary accounting, they contain equal internal energy. Their capacity to perform work, however, is profoundly different. The incoherent mixture is already completely disordered across the two energy levels. No reversible cyclic control can lower its average energy, so none of that energy is available as ergotropy, the maximum work extractable through an ideal controlled transformation. The coherent state has the same energy populations, but its phase relationship makes the state pure and directionally organized within its quantum state space. A carefully timed control pulse can rotate it completely into the lowest energy state, transferring the entire initial average energy into an external work storage system. The useful difference was therefore not visible in the energy distribution alone. It was hidden in the coherence connecting the levels. Experiments with single-spin systems have directly separated coherent and incoherent contributions to ergotropy and observed that increasing coherence can increase extractable work even when the level populations are held fixed. This does not mean coherence creates energy. Preparing and controlling the coherent state requires physical resources, and imperfect knowledge or environmental noise can destroy part of its work value before extraction. Work also depends on which operations are available. A state useful under precise global control may yield less under slow, local, or restricted manipulations. Recent studies emphasize that ergotropy measures organized energy rather than energy alone, and that extracting it carries its own energetic and control costs. You might compare the two states to rooms containing the same number of people. In one room, everyone moves randomly and no coordinated motion can turn a wheel. In the other, the crowd moves in step, carrying no more total energy but possessing a direction that can be harnessed. Quantum physics places that hidden coordination inside phase relationships too delicate for an ordinary energy measurement to notice. The lesson is that internal energy tells you how much motion a system contains. while usable work tells you how much of that motion can still be guided. Two states may therefore weigh the same on nature's energetic scale, and yet hold entirely different futures. One filled with energy that can be released, the other with energy that has nowhere useful left to go. Quantum system can possess negative conditional entropy. Imagine learning everything about one half of a system and discovering that your uncertainty about the other half has fallen below zero. Not merely vanished, but become a resource you can spend. In classical information theory, conditional entropy measures how much uncertainty remains about one object when another is already known. It may fall to zero when the known object determines the unknown one perfectly, but it cannot become negative. Knowing the second card cannot make you know more than everything about the first. Entangled quantum systems break that boundary. Take two particles in a pure, maximally entangled state. The pair as a whole can be known perfectly, meaning the complete state has no entropy, while either particle examined alone appears completely random and carries 1 unit of entropy. When you ask how much uncertainty remains about Alice's particle given access to Bob's, the quantum definition subtracts Bob's local uncertainty from the uncertainty of the complete pair. The result is negative. Nothing has acquired less than no physical disorder, and no observer possesses a probability smaller than zero. The negative value means that Bob's quantum side information is more powerful than any classical description of Alice's system could be. The significance becomes concrete in a protocol called quantum state merging. Alice and Bob share many copies of a distributed quantum state, and Alice wants to transfer her part to Bob while preserving all correlations with anything outside their laboratories. When the conditional entropy is positive, Alice must send quantum information. When it is negative, she can complete the transfer using classical communication and, instead of consuming entanglement, finish with additional shared entanglement available for future tasks. The magnitude of the negative entropy measures how much of that resource can be gained per copy in the ideal large-scale limit. Negative conditional entropy is therefore not a mathematical curiosity, but an operational advantage, associated with protocols including state merging, entanglement distillation, superdense coding, and private randomness generation. Yet not every entangled state possesses it. It identifies a particularly useful subset whose correlations are strong enough to push the conditional quantity below zero. Researchers have developed measurable witnesses that can certify this property without reconstructing every detail of the state. You should not picture negative entropy as a cold substance stored inside a particle or as a violation of thermodynamics. It describes information in a relationship. Alice's subsystem alone looks uncertain. Bob's subsystem alone looks uncertain, but the joint state contains a structure so complete that Bob's share does more than help identify Alice's. It gives the pair a surplus capacity for future quantum communication. In the classical world, side information can reduce the price of learning something to zero. Entanglement allows the price to pass through zero and become a reward. The system does not merely answer the question you were going to ask. It leaves behind a new connection, as though understanding one part of reality had returned more information than the act of understanding required. An event can be inside one, causal history, and outside another. A signal may be able to reach an event in one branch of reality while being physically forbidden from reaching the same event in another. To understand how this could happen, you first need to picture a light cone, the invisible boundary that separates everything an event can influence from everything lying beyond its causal reach. An event inside your future light cone can, in principle, receive a message from you traveling no faster than light. An event outside it is too distant or too soon. Reaching it would require faster than light communication. In classical general relativity, these boundaries are shaped by matter because mass curves space-time and changes how light travels. A ray passing near a massive body experiences a gravitational delay, arriving slightly later than it would through empty space. Now imagine that the body producing this delay is not located in one definite place. It is prepared in a quantum superposition of two positions. In one branch, the mass lies close enough to the signal's route to delay it strongly. In the other, it lies farther away and produces a weaker delay. A 2026 theoretical study found that, in such a model, the light cone boundary itself becomes dependent on the quantum state of the source. Two fixed events can then have a time-like relationship in one branch, meaning a causal signal can connect them, while being space-like separated in another, meaning no ordinary signal can pass between them. The event is not half real or displaced into a fantasy universe. What becomes indefinite is whether it belongs inside the causal future of the earlier event at all. A related peer-reviewed proposal showed that placing a massive body in a spatial superposition could place the temporal order of distant operations into a coherent quantum combination, because each position of the mass produces a different gravitational timing structure. The authors described a possible Bell-type test for temporal order, although carrying out such an experiment would be far beyond present capabilities. This does not allow anyone to send a message outside the light cone, rewrite an event, or choose which causal history becomes real. In every branch, signals still obey the causal boundary belonging to that geometry. The strangeness appears only when the geometries remain coherent, so that the complete system cannot be reduced to an ordinary lottery in which one classical spacetime secretly existed all along. Any attempt to learn the mass's position too strongly would reveal which geometry was present and destroy the interference needed to test their quantum relationship. The idea also remains theoretical. No experiment has yet placed a sufficiently massive gravitational source into the required controlled superposition and measured a light cone becoming quantum. Still, the model exposes something profound about causal location. You normally imagine that an event either lies within another event's reach or it does not, as though causality were an unchanging map printed beneath the universe. But if the matter drawing that map can occupy several quantum configurations, the boundary between reachable and unreachable may also lose its single classical position. An event could belong to one causal history while standing beyond the edge of another, and the universe may preserve both possibilities until the geometry itself leaves a record. What you call after, reachable, and connected may therefore depend not only on where events occur, but on the quantum condition of the matter that quietly shapes the roads between them. Quantum correlations may exist that cannot fit into any ordinary timeline. Give two observers a simple guessing game, and their answers may reveal correlations that no possible arrangement of Alice first, Bob first, or neither first can explain. Imagine that Alice and Bob enter isolated laboratories and each receives a random bit. On every round, another random instruction decides whose task matters. Sometimes Alice must guess Bob's bit, and sometimes Bob must guess Alice's. If Alice definitely acts first, she cannot know the bit Bob receives later, although she can send her own bit forward so Bob succeeds whenever his guess is required. If Bob definitely acts first, the situation reverses. Even if the order changes randomly from round to round, any ordinary causal timeline limits their average success to 3 correct rounds out of 4. This limit is a causal inequality, a constraint obeyed by correlations compatible with some definite or probabilistic order of events. In 2012, researchers introduced the process matrix framework, which assumes that ordinary quantum mechanics works inside each local laboratory, but does not assume that the laboratories must be connected by a predefined global causal structure. Within that framework, they found a valid mathematical process allowing Alice and Bob to succeed roughly 85% of the time, exceeding the classical causal limit. The resulting correlations cannot be decomposed into any mixture of Alice influencing Bob, Bob influencing Alice, or the two remaining causally independent. This is stronger than merely hiding which order occurred. If a coin secretly selected one timeline on every trial, the causal inequality would still hold. Violating it means that no ordinary timeline assignment, even one that changes randomly, can reproduce the observed statistical pattern. The process does not need to produce a logical contradiction. and neither observer can necessarily use it to create a message that becomes its own cause. Instead, the correlations fit together globally in a way that refuses to be drawn as a directed sequence of influences. You can imagine trying to place every conversation in a novel onto numbered pages, only to discover that one character's answer requires another character's question to be earlier, while that second question can be explained only if the first answer came earlier. The story remains statistically consistent, yet no page order accommodates all of its relationships. Researchers call processes producing such statistics non-causal in the technical sense of violating a causal inequality. However, an essential scientific caution remains. Although the process matrix framework permits them mathematically, whether every such process can be physically realized is unresolved. Present laboratory demonstrations have mainly involved the quantum switch and related controlled order experiments. Those processes are causally non-separable, but the ordinary quantum switch by itself does not violate the original causal inequalities, meaning its observable correlations can still admit certain definite order explanations when only input-output statistics are considered. More recent work continues to investigate the strongest correlations compatible with quantum processes and the limits separating them from even more general logically consistent possibilities. The importance of the idea is therefore not that scientists have already built a machine operating outside time. It is that quantum theory contains a mathematically disciplined way to discuss correlations without first providing the events with one universal schedule. In ordinary reality, you explain patterns by drawing arrows. This happened, therefore that followed. Process matrices ask whether the correlations could be more fundamental than the arrows themselves. Perhaps a timeline is not always the stage on which quantum events perform. Perhaps, at the deepest level, the correlations arrive first, and the familiar order of moments emerges only when the universe becomes large, stable, and classical enough to arrange them into a story you can read from beginning to end. Different quantum observers may divide the same universe into different systems. There may be no single, observer-independent answer to the question of where one quantum system ends and another begins. You normally divide reality without hesitation. This particle is the object, that apparatus is the observer, and everything beyond them is the environment. Quantum theory often begins with the same division, assigning each part its own collection of measurable properties before describing how the parts interact. But a physical observer is also made of quantum matter, and once that observer is used as an internal reference frame, rather than treated as something outside the universe, the division can change. Consider three particles floating in an otherwise empty region, with no external ruler defining absolute position. An observer associated with particle A describes B and C through their positions relative to A. From this perspective, certain relational quantities naturally belong to B, others belong to C, and the two can be treated as distinguishable subsystems. An observer associated with B builds a different description, using A and C relative to B. This transformation does more than replace one set of coordinate numbers with another. The measurable quantities grouped together as one subsystem in A's perspective may be reorganized across several subsystems in B's perspective. Research on the quantum relativity of subsystems shows that different quantum reference frames can induce different sets of observable algebras, that collections of physical questions assigned to each part, and can, therefore, produce frame-dependent notions of subsystem separation and locality. Quantities that belong to commuting, independently measurable parts before the relational constraints were imposed may no longer retain the same separation from another internal perspective. This means the observers are not merely disagreeing about an object's position, they may disagree about which variables together constitute the object. One observer can describe a degree of freedom as belonging to the system under study, while another includes that same degree of freedom in the reference frame, or in what functions as the environment. More recent frameworks have developed reversible rules for translating descriptions between relative subsystems, and emphasize that changing quantum frames can alter how superposition, correlations, and the very division into accessible parts appear, while preserving the relational predictions that observers can ultimately compare. Related theoretical work suggests that even whether a subsystem appears isolated or open to an environment, as well as how heat, work, and entropy are assigned to it, may depend on the quantum frame used to partition the whole. None of this means that a person can divide the universe however they like, or make a detector disappear by changing perspective. The permitted divisions follow precise symmetry constraints and must translate consistently into one another. If two observers reunite their records and correctly transform the measurements made in their respective frames, they cannot obtain incompatible operational results. The disagreement concerns the internal organization of the description, not the existence of arbitrary personal realities. These ideas also remain part of an active theoretical program, rather than a laboratory demonstration that human observers literally see different collections of objects. Yet, they expose how much classical intuition is hidden in the word system. You tend to imagine the universe as a box filled with pieces whose boundaries were drawn before any observer arrived. Quantum reference frames suggest that the complete universe may come first, while its division into systems is relational, created by the physical perspective from which one part becomes a reference for the rest. What you call an object may therefore be less like an isolated island and more like a region defined by the map you are physically able to draw. Change the quantum observer and the universe remains whole, but the lines showing where its pieces begin may quietly rearrange themselves. Nearly impossible measurement result can carry enormous information. The detector that almost never responds may become the most informative instrument in the room on the rare occasion that it finally clicks. Suppose you were trying to measure an extremely small phase shift in a beam of light. You send the light through an interferometer and adjust the paths so that they cancel almost perfectly at one output, creating a nearly dark port. With no shift, a photon reaching that detector is extraordinarily unlikely. A tiny change in the unknown phase can disturb the cancellation and alter that small probability by a large fraction. The detector still clicks rarely, but each click now provides unusually strong evidence about the value of the hidden phase. Physicists quantify this sensitivity using Fisher information, which measures how rapidly the probabilities of possible outcomes change when the unknown parameter changes. A common result that changes only slightly with the parameter may carry little information. A rare result whose probability rises or falls extremely sharply can carry a great deal of information when it occurs, because observing it strongly changes which parameter values remain plausible. This is not exclusive to quantum physics, but quantum interference allows experiments to engineer exceptionally sensitive rare outcomes through coherent cancellation and post-selection. The system first experiences the unknown transformation, then a filtering measurement keeps only a chosen outcome. The surviving state may be far more sensitive to the parameter than the original state when information is counted per retained measurement. Research in post-selected quantum metrology has shown that Fisher information per costly final measurement can exceed what is available from optimized non-post-selected strategies under appropriate conditions, with the advantage tied to non-commuting quantum measurements and non-classical quasi-probability structure. A newer way to understand the effect is as information compression. Many probes pass through the inexpensive early stage. Most are rejected, and a small surviving fraction carries a concentrated share of the information into a detector that may be slow, noisy, easily saturated, or expensive to operate. A general theory of post-selected compression channels has identified ideal cases in which the information lost through filtering can be made arbitrarily small, even though only a small portion of the output states proceeds to the final measurement. But the nearly impossible result is not a source of unlimited knowledge. Its enormous information per successful event is normally balanced by the long wait for that event. If you count every prepared probe, every failure, all discarded data, and all experimental costs, Post-selection does not automatically defeat the fundamental precision available from the complete experiment. A protocol that produces one exceptionally informative click after a million attempts may still perform no better overall than a protocol extracting smaller amounts of information from every attempt. The advantage becomes meaningful when the true bottleneck is not preparing probes, but reading them. When detectors saturate, storage is limited, or detailed processing is costly. Noise and imperfect alignment also matter greatly, because the same near cancellation that makes the rare outcome sensitive can make it fragile. The result should therefore not be interpreted as a particle announcing a gigantic hidden value, or as nature placing an entire answer inside one miraculous event. What becomes enormous is the change in your knowledge produced by that event. Most outcomes leave many explanations alive. The rare click destroys nearly all of them at once. You are accustomed to trusting repetition, to believing that truth speaks through what happens most often. Quantum metrology reminds you that frequency and meaning are not the same. Sometimes the quietest detector waits through thousands of empty moments, and then one improbable signal arrives, carrying the information that all the ordinary outcomes were unable to reveal. A weak measurement can reveal a history that no single particle actually followed. Draw two openings in a barrier. Release photons one at a time, and after thousands of trials you can reconstruct elegant curved paths flowing from the slits toward the interference pattern, even though quantum mechanics never says that any individual photon traveled along one of those complete curves. In a landmark two-slit experiment, researchers used single photons from a quantum dot source and measured their transverse momentum so gently that the interference pattern was not erased. They repeated the procedure at many positions beyond the slits, then sorted the weak momentum readings according to where the photons were finally detected. By linking the average momentum directions from one plane to the next, they produced families of smooth streamlines that bent around dark interference regions and converged toward bright fringes. The paths closely resembled trajectories associated with the flow of the quantum wave, providing an operational picture of how different detected subensembles propagated through the interferometer. Yet the word trajectory must be handled with care. No camera followed one photon continuously from source to screen, and the curve labeled as a path was assembled from weak data contributed by many separately prepared photons. One group provided the average momentum near one location, another group contributed information farther downstream, and final position measurements selected which trials entered each reconstruction. The finished curve therefore summarizes conditional statistics across an ensemble. It is not a diary recovered from one particle. A particular photon may contribute one faint reading to the data, but it does not leave behind the entire sequence needed to draw the complete line. This is why the experiment can reveal a history that no identifiable particle actually followed from beginning to end. The reconstructed streamlines are scientifically meaningful because they map the flow of probability or optical energy through the apparatus, and within certain interpretations they can be related to Bohmian trajectories. Other analyses note that closely related weak momentum patterns can also be understood through classical wave optics, emphasizing that the data alone do not force one literal account of an individual photon's hidden journey. Weak measurement does not remove the uncertainty principle by secretly observing everything without consequence. It trades disturbance for vagueness. Each interaction reveals very little, and clarity appears only after repetition and statistical reconstruction. The resulting picture is neither fictional nor a conventional track through space. It is a history belonging to a selected population, formed from the relationship between preparation, weak probing, interference, and final detection. You are accustomed to believing that an average path must be the blurred version of paths that individual objects really traveled. Quantum physics allows the reverse possibility. The collective flow can be precise and beautifully structured even when no single member of the ensemble owns the complete story. The path exists as a reliable pattern in the data, while the individual photon passes through the experiment without surrendering a continuous biography. The path of a quantum object may depend on which trace you decide to count. Photon can brush past a vibrating mirror, rotate a polarization marker, shift an arrival time, or disturb a nearby probe, and each surviving trace may tell you a different story about where the photon was. In classical reasoning, these clues should converge on one hidden route. Mud on a shoe, a fingerprint on a door, and an image from a camera are different records of the same journey. Quantum interferometers are less forgiving because traces are created through physical interactions, and different interactions couple to different parts of the quantum state. In a nested interferometer, for example, several paths can overlap and cancel before the photon reaches the detector. Researchers may mark each arm by vibrating its mirror at a unique frequency, then examine the final beam for those frequency signatures. Another experiment might attach path information to polarization, phase, momentum, or the state of a small environmental probe. These methods do not simply read a route already written beneath the interference. They ask different physical questions, preserve or destroy different coherences, and extract different portions of the available witch path information. Work on multidimensional witch path information has shown that separate detection methods can reveal only partial aspects of the path record, and that the accessible information depends on phases and beam splitter settings within the interferometer. One influential proposal defines a particle's past as the regions where an extremely weak local interaction leaves a non-zero trace in an ensemble of identically prepared and post-selected systems. Applied to nested interferometers, this rule can assign presence to disconnected internal regions even when the entrance and exit traces cancel, producing a history unlike one continuous classical path. But this criterion is not universally accepted as the unique meaning of where the particle was. Critics point out that weak measurements still perturb the system, that weak values describe selected ensembles rather than individual particles, and that a non-zero response of a chosen pointer does not automatically prove literal particle presence. Another interaction could be insensitive where the first one responds, or could register a trace that the first criterion overlooks. This does not reduce the experiment to subjective opinion. Once you specify the preparation, coupling, observable, final selection, and detector, quantum theory predicts the statistics precisely. What remains unsettled is whether one of these records deserves to be promoted into the single true path independent of the measurement used to define it. The photon has not changed its past merely because a scientist prefers one detector. Rather, the phrase "the path" may be incomplete until you state which physical trace counts as evidence of presence. At quantum scales, histories are not always discovered like roads viewed from above. They are inferred from marks produced by particular encounters, and different kinds of marks can illuminate different structures within the same event. You may begin by asking where the object traveled, expecting nature to answer with one line. The experiment may instead ask you a quieter question in return. Which footprint did you decide was capable of proving that it had been there? Entanglement can be borrowed without the original supply appearing to shrink. Imagine taking a usable entangled pair from a shared quantum reservoir, completing the task you needed it for, and then examining the reservoir so carefully that it appears almost unchanged. This phenomenon is called entanglement embezzlement, and its name is deliberately provocative because no ordinary catalyst should be able to supply a resource while returning in nearly the same condition. Alice and Bob begin far apart, each holding one half of a specially constructed, very high-dimensional entangled state. Its entanglement is not distributed evenly. Instead, it is spread through a long hierarchy of components whose weights decrease gradually, so no single layer contributes very much by itself. By performing only carefully coordinated local transformations on their own systems, Alice and Bob can reshape this broad distribution and produce an additional target entangled state between new particles. They require no quantum communication during the conversion and, in the ideal description, no classical message telling one side how the other operation turned out. Afterward, The original reservoir is not exactly the state it was before, but the disturbance can be made arbitrarily difficult to detect by choosing a sufficiently large embezzling state. The borrowed entanglement is paid for through tiny changes scattered across an enormous number of components, much as removing a small quantity of water from a vast, gently sloping lake may barely alter the visible shoreline. Van Dam and Hayden showed that such states can approximately support transformations between arbitrary pure bipartite entangled states, and later work has characterized the families capable of this behavior, finding that successful universal embezzlers must share the essential broad structure of the original construction. This does not violate the rule that local operations cannot create entanglement from nothing. The reservoir truly changes, and the total resource accounting still reflects the entanglement transferred into the target. The illusion appears because ordinary closeness between two enormous quantum states does not guarantee that every resource hidden inside them is nearly equal. A very small global disturbance, distributed over a space of huge dimension, can contain enough cumulative change to finance a modest entangled pair. Exact embezzlement with a finite untouched catalyst is not what the protocol delivers. The transformation is approximate, and reducing the error requires a reservoir of increasing size. Repeated borrowing would also accumulate damage, eventually making the change observable and weakening future performance. Preparing, storing, and controlling such a delicate, high-dimensional state would itself demand substantial physical resources. So this is not a practical source of unlimited free entanglement. Yet the principle exposes a weakness in the way you naturally judge change. You tend to compare a system before and after, see that almost every visible feature agrees, and conclude that almost nothing was consumed. Quantum information warns that resemblance can be misleading when a resource is spread thinly across an immense structure. The reservoir does shrink, but not in one place you can point to. Its loss is diluted through countless faint adjustments, allowing entanglement to be borrowed in a way that leaves no dramatic wound. Only a nearly invisible change written across the whole. A quantum state can hide entanglement so well that it looks almost untouched. Remove a single qubit from an enormous quantum state, leave every other particle physically untouched, and the amount of entanglement assigned to what remains can collapse by an arbitrarily large amount. This is known as entanglement locking, and it reveals that quantum correlations are not always stored like independent threads that can be counted one by one. In specially designed states, sometimes called flower states, two large systems share correlations whose useful structure depends on one small control subsystem. That control qubit helps preserve which coherent arrangement links the larger parts. While it is available, an observer who knows how to include it in the full description may find that creating the state would require a large supply of entanglement, or that the state possesses a large value according to measures such as entanglement of formation or entanglement cost. Now discard or measure that one qubit without retaining the relevant outcome. The remaining systems have barely been touched in the ordinary mechanical sense. Their particles were not individually measured, separated, heated, or replaced. Yet, the small operation destroys the label or phase relationship that allowed the many global components to align into a highly entangled description. What remains becomes a mixture of alternatives that are much harder, or sometimes impossible, to use as the original entanglement resource. Horodecki, 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 and Oppenheim showed that several important entanglement measures are lockable in precisely this way. Measuring or losing one qubit can reduce their value by an amount that grows without bound as the dimensions of the untouched systems increase. They also showed that not every measure behaves this way. The relative entropy of entanglement, for example, does not suffer the same arbitrarily large single qubit collapse. The result does not mean that one qubit literally contains all the entanglement of thousands of other degrees of freedom. The large systems carry the correlations, but the small subsystem controls how those correlations can be coherently interpreted and accessed. It functions less like a box containing the treasure and more like the orientation of a map. Remove one tiny compass mark, and an enormous landscape remains in front of you, while the route through it disappears. Nor does the state remain mathematically identical after the qubit is measured or discarded. A physical change has occurred, and information has been lost to the environment or measurement record. What makes locking remarkable is the imbalance between the size of the intervention and the size of the change in the quantified resource. Nearly the entire material system survives, yet its entanglement can appear to fall from vast to modest, because one small piece held the coherence that made the global pattern usable. This also teaches you to be cautious when treating the amount of entanglement as though it were a simple substance with one universally agreed volume. Different measures answer different operational questions. How much entanglement is needed to create a state? How much can be extracted? Or how strongly the state differs from all separable states? And some of those answers can be extremely sensitive to a tiny missing subsystem. The entanglement was never painted visibly across the particles. It was folded into the way all the pieces referred to one another, touch almost nothing, lose one quiet key, and the state can look nearly unchanged, while an entire hidden architecture of quantum connection closes beyond reach. Two systems can be entangled, but unable to produce usable entangled pairs. Entanglement can be unquestionably present between two distant laboratories, and still remain impossible to refine into even one clean entangled pair that Alice and Bob can reliably use. Usually, when noise damages shared entanglement, the observers collect many imperfect copies and perform a process called entanglement distillation. Alice manipulates only the particles in her laboratory. Bob manipulates only his, and they exchange ordinary messages about their measurement results. They discard unsuccessful copies and keep the rare successful ones, gradually concentrating weak, noisy correlations into fewer pairs that approach a nearly perfect Bell state. Those purified pairs can then support demanding tasks such as faithful quantum teleportation. It would be natural to assume that every genuinely entangled state contains at least a small amount of this recoverable resource. Quantum theory says otherwise. Certain mixed states are entangled. Their joint statistics cannot be reproduced by imagining that Alice and Bob merely possess independently prepared particles, connected by ordinary shared randomness, yet no matter how many identical copies they collect. Local operations and classical communication cannot distill them into pure entangled pairs. This condition is called bound entanglement. One important family is identified using a test known as partial transposition. The test mathematically reverses part of the description belonging to one observer. Many ordinary distillable states become unphysical under this reversal, revealing a negative feature that signals accessible entanglement. Some higher dimensional states remain mathematically positive under the test while still being provably inseparable. Local processing and classical messages cannot turn this positive form into the negative form possessed by a Bell pair, so the desired pure pair remains unreachable. The Horodecki family established this distinction in 1998, showing that entanglement divides into a free form that can be distilled and a bound form that cannot be converted into singlets for quantum communication by the permitted procedures. This does not mean that the particles are only classically correlated, or that the entanglement is an error in the calculation. The state lies outside the entire set of separable states, and producing it generally requires quantum resources. What is missing is not entanglement itself, but a legal route for concentrating it. You might imagine valuable metal spread through a material in a chemical form that no available furnace can separate. The value is physically present, yet the permitted tools cannot release it as a usable ingot. Bound entanglement behaves in a similar way. Its correlations are woven so deeply into noise and global structure that every local attempt to purify them fails to isolate a clean pair. An experimental 4-qubit realization of a bound entangled Smolin state confirmed that entanglement can be present while remaining non-distillable under separated local operations. Although that multipartite state possesses special unlocking properties when the rules about which parties may meet are changed. The restriction is therefore operational rather than mystical. Change the available cooperation, introduce another resource, or ask the state to perform a different information task, and it may reveal abilities that ordinary distillation overlooks. But under the original conditions, Alice and Bob can share an unlimited supply of genuinely quantum correlation and still fail to manufacture one standard pair. This is what makes bound entanglement so unsettling. Nature can create a connection that is real enough to resist every classical explanation, yet so tightly bound inside the whole state that neither observer can extract the simple connection they were searching for. Entanglement, then, is not always a currency that can be melted down into identical coins. Sometimes it exists more like an inheritance locked inside a structure whose value is undeniable, while the key required to spend it is absent from the world Alice and Bob are allowed to use. Useless entanglement can become useful when combined with more useless entanglement. Two quantum resources that each produce exactly zero usable entanglement can be placed together and suddenly yield a distillable pair, as though two locked doors had somehow become one another's keys. This phenomenon is called superactivation of bound entanglement. It begins with states that are individually non-distillable under the allowed pattern of local operations and classical communication. Give the observers one of these states, even in many copies, and they cannot isolate the high-quality entangled pair needed for ordinary teleportation. Give them a second carefully chosen bound entangled resource, and the combined system can contain a root that neither resource possessed alone. The effect is not simple addition. 0 units of distillable entanglement from the first state and 0 from the second might seem certain to remain 0. But quantum resources do not always obey that ordinary arithmetic. Their usefulness depends on the global structure of the correlations and on how the inaccessible information in one state complements the inaccessible information in the other. One state may contain correlations blocked by a particular division of the observers, while the second connects the parties across a different division. When the prescribed measurements and messages are performed across the combined network, each state supplies relational information missing from the other. Ambiguities that prevented distillation can cancel, and a selected pair of distant parties can be left with entanglement that is now known, controlled, and usable. Shaw, Smolin, and Thaplial proved that in a multipartite setting, two non-distillable bound entangled states can combine into a distillable state, establishing a genuine superadditivity of distillable entanglement. The claim is not that any two useless states will work. Superactivation requires states with compatible correlation structures and an appropriate protocol, nor does it create entanglement from nothing. Both starting states were already entangled, and the joint procedure reorganizes a resource that had been inaccessible rather than producing a new one without cost. Measurements, feedback, classical communication, precise preparation, and possession of both states are all part of the complete physical accounting. The phenomenon has also been demonstrated experimentally in a continuous variable optical system. Researchers prepared 2 copies of a 4-party unlockable bound entangled state and applied measurements and feedback across the combined resources. Neither state alone supplied the desired distillable Einstein-Podolsky-Rosen pair under the protocol, but together they allowed such a pair to be extracted between designated subsystems. This does not permit faster-than-light messages because the distant parties still need ordinary communication before the extracted correlations can be interpreted and used. It also does not make the original resources endlessly reusable. The procedure consumes or changes the states from which the distillable pair is obtained. What superactivation overturns is the assumption that the usefulness of a collection must equal the sum of the usefulness visible in each item separately. In classical life, 2 broken engines rarely assemble themselves into a working one merely because they are placed side by side. Quantum information can behave differently because a state's weakness may be relational. What one resource lacks, another may supply not as an extra object, but as a missing pattern of correlation. The first state cannot explain its own hidden structure, and neither can the second. Yet together, they provide enough context for part of the entanglement to become free. You begin with two resources that appear operationally silent, combine them, and hear a signal that existed in neither one alone. The deeper lesson is that useless may not be an intrinsic property of a quantum state. It may describe only what that state can accomplish in isolation. Place it beside another failure shaped in the right way, and the boundary between trapped and usable can suddenly open, revealing that quantum power may live not only inside resources, but in the unexpected ways their limitations fit together. Entanglement can act like a catalyst that returns almost unchanged. Quantum transformation that is completely forbidden can become perfectly possible when Alice and Bob temporarily borrow an entangled state. And, unlike the nearly invisible damage involved in entanglement embezzlement, this catalyst can return exactly as it began. Imagine that Alice and Bob share a pure entangled state they want to convert into another state using only operations performed in their separate laboratories and ordinary messages exchanged between them. Quantum theory imposes strict rules on such conversions. It is not enough for the starting state to contain more entanglement according to one simple number. Its correlation weights must be ordered in the right way so that each stage of the target distribution can be built without locally increasing the resource. Some pairs of states cannot be ranked in this manner. The first is not clearly more useful than the second, and the second is not clearly more useful than the first. They are called incomparable. Neither can be transformed deterministically into the other under the permitted local procedure. Daniel Jonathan and Martin Planio discovered that adding a carefully chosen entangled pair can change this verdict. Alice combines her half of the desired state with her half of the catalyst, while Bob does the same on his side. The combined distributions now possess a different ordering, and the previously forbidden conversion becomes allowed. At the end, the main state has changed into the intended target, while the catalytic pair is returned in precisely its original entangled state and remains separate from the output. It has not donated a hidden fragment of itself, lost a little purity, or spread tiny damage across a huge number of levels. In the ideal protocol, it is genuinely unchanged and can in principle assist the same kind of transformation again. The catalyst works because the rules governing local state conversion apply to the complete combined pattern, not to the target state and auxiliary state independently. Multiplying the two correlation structures creates new intermediate balances, allowing Alice and Bob to move probability weight in a sequence that was unavailable before. When the auxiliary state is removed from the calculation at the end, its own structure is exactly restored, yet the main system has crossed a boundary it could not cross alone. This does not generate entanglement from nothing or permit every desired conversion. The total transformation must still obey fundamental resource constraints, and only particular catalysts fit particular incomparable states. The catalyst also has to be present physically, protected from noise, and manipulated with the main system, so obtaining and maintaining it carries real experimental cost. More recent work has clarified how dramatically catalysts enlarge the possible transformations between pure entangled states, and has shown that entanglement entropy acquires a powerful operational role when suitable catalysts are available. Still, the central phenomenon remains almost unsettling in its simplicity. If you inspect the starting system alone, the transformation is impossible. If you inspect the catalyst before and after, nothing has changed. Yet the impossible event has occurred between those two observations. The catalyst did not pay for the transformation by being consumed. Its presence changed the landscape of what local actions were allowed to accomplish. It is as though Alice and Bob faced a staircase whose steps were spaced too widely for either of them to climb, then placed a borrowed platform between the steps, crossed the gap, and returned the platform to exactly the height and condition in which they found it. The platform contains no record of the journey, but without it, the journey could never have happened, revealing that in quantum physics, a resource can matter not only through what it gives away, but through the possibilities its temporary presence makes reachable. A separate quantum state can enable a transformation without being consumed. Particle can be forbidden from entering a coherent superposition by energy conservation, yet a separate quantum state can quietly provide the missing reference needed to complete the transformation while appearing unchanged afterward. Suppose a small system begins in a definite energy level and you want to place it into a controlled combination of two different energies. An operation capable of doing this must preserve a precise phase relationship between the alternatives. But a perfectly energy-conserving device cannot create that phase reference from nothing. It would be like trying to synchronize a clock in a universe containing no other clock. The transformation becomes possible if you introduce an auxiliary reservoir already possessing coherence across many energy levels. The target system can exchange energy with this reservoir through a globally energy-preserving interaction. When the target rises to the higher energy alternative, the reservoir shifts downward by the corresponding amount. When the target remains lower, the reservoir follows another component of its state. Because the reservoir began as a broad coherent ladder rather than one definite energy, these alternatives can remain phase-related, allowing the target to emerge in the desired superposition. Johann Oberg proposed that such a reservoir could act catalytically. It could enable coherent operations repeatedly, without an obvious reduction in its local ability to serve as a phase reference. This sounds as though the coherence has been used without being spent, but the full truth is more delicate. After one use, the reservoir's reduced state can remain effectively the same for the relevant operation, while correlations have formed between it and the system it assisted. After several uses, the different target systems can also become correlated through their shared reservoir. If you inspect only the reservoir by itself, it may appear unchanged. If you inspect the complete global state, the history of its use has been written into those correlations. Later analyses showed that repeated use cannot always be treated as a sequence of perfectly independent transformations, and that accuracy or thermodynamic cost can deteriorate when the accumulated correlations are properly included. Modern catalytic frameworks make this distinction explicit. They allow auxiliary states to retain their individual marginal forms while correlations develop among them. And under those rules, catalysts can enable an extraordinarily broad range of coherence transformations with arbitrarily small error. The resource has not disappeared from any one catalyst's local description, but part of its usefulness has migrated into a collective relational structure. This is not free coherence, perpetual work, or a violation of energy conservation. The reservoir must first be prepared in a coherent state. The global interaction must conserve energy, and restoring an uncorrelated, reusable collection can require additional resources. The apparent non-consumption depends on what you agree to count. The local state may return, while independence from everything it touched does not. That difference is easy to overlook because classical catalysts are usually judged by their visible material condition. A chemical catalyst may finish with the same molecular structure and be ready for another reaction. A quantum catalyst can finish with the same local measurement statistics, yet carry invisible correlations connecting it to past systems. It resembles a tuning fork that continues to produce the same note after helping several instruments synchronize, while those instruments now share timing relationships that did not exist before. The fork appears untouched, but the world around it has acquired a new pattern. Quantum catalysis therefore forces you to ask a deeper accounting question. When a state enables change without losing any locally measurable quantity, has it truly remained unchanged, or has the cost been written into relationships that no examination of the catalyst alone can see? A many-particle system can avoid thermal equilibrium without being frozen. Scatter interacting particles across a disordered quantum landscape, and you can create a system that keeps moving, keeps changing, and keeps building new correlations, while stubbornly refusing to forget where it began. Most isolated many-particle systems are expected to thermalize. A particle carrying extra energy collides with its neighbors. Those neighbors influence others. and information about the starting arrangement spreads until no small region retains a useful memory of the original pattern. Eventually, local measurements become consistent with an equilibrium temperature, even though the complete system never touched an external heat bath. Many-body localization offers a remarkable exception. Strong disorder makes the energy landscape different from one location to the next, so transitions that would normally move particles or spin excitations through the system become badly mismatched. One region may be ready to release energy, while its neighbor cannot accept exactly that amount, causing transport pathways to interfere and weaken. Interactions remain present, but they cannot efficiently carry particles and energy across the entire system. In a major experiment, researchers loaded interacting fermionic atoms into a one-dimensional quasi-random optical lattice and prepared an alternating density pattern. Under weak disorder, the pattern faded as the atoms redistributed and thermalized. Under sufficiently strong disorder, a substantial part of the initial pattern survived, providing evidence that the interacting system retained local memory instead of settling into ordinary equilibrium. Trapped ion experiments later observed related signatures in disordered interacting spin systems, including memory of initial conditions together with evidence that entanglement continued to develop over time. This last detail is what prevents you from picturing many-body localization as a collection of completely frozen particles. The system is not a photograph. Its components continue accumulating phases, influencing nearby degrees of freedom, and becoming entangled through weak interactions. Theory describes the localized regime using quasi-local conserved quantities, sometimes called L-bits, which resemble dressed versions of local spins. Each one is concentrated around a particular location but possesses faint tails extending into the surrounding system. Their approximate values remain preserved, preventing the dynamics from erasing all local information, while interactions between their distant tails slowly cause dephasing and a logarithmic growth of entanglement. The particles can therefore lose the simple coherence of their initial product state without reaching the thermal state predicted from energy alone. Local observables may relax partially, entanglement may spread, and the internal quantum state may become highly complicated, yet energy and information remain unable to explore the system freely. Scientific caution is essential here. Experiments observe finite systems over finite times, and the long-term stability of many-body localization remains debated for higher dimensional systems. Very large samples and situations where rare thermal regions could gradually destabilize localization. The clearest theoretical and experimental evidence concerns strongly disordered, effectively one-dimensional systems under carefully controlled isolation. Many-body localization is not a universal escape from thermodynamics, and even weak contact with an environment can eventually erase its protection. Still, the phenomenon reveals that motion and equilibrium are not opposites. A system can evolve endlessly without visiting the overwhelming majority of states available at its energy. It can change without becoming typical, communicate locally without sharing everything globally, and carry the memory of its beginning inside countless, slowly interacting fragments. You usually imagine that time washes structure away because activity mixes everything together. Many-body localization suggests a quieter possibility. The system may remain alive with internal motion while disorder turns its possible future into a maze whose corridors never quite lead to equilibrium. Two states can exist in the same system yet be dynamically separated forever. Build a quantum world on the surface of a donut, and two states with the same energy and identical local appearance can remain separated by a difference that no local action can erase. This is the central idea behind topological sectors in models such as Kitaev's toric code. The system consists of qubits arranged along the edges of a two-dimensional lattice whose opposite boundaries are connected, giving the surface the topology of a torus. Its lowest energy states obey the same local rules around every vertex and face. If you examine any small region, measure a few neighboring qubits, or gently disturb one limited patch, the different ground states appear essentially identical. Their distinction is not stored in one particle, one corner, or one conventional order parameter. It is encoded globally in how invisible loops wind around the two non-contractible directions of the torus. One state may carry one pattern of global loop values, while another carries a different pattern, even though both satisfy every local energy constraint and possess exactly the same ground state energy in the ideal model. Kitaev showed that the toric code on a torus has 4 such ground states, and that their degeneracy is robust against local perturbations, with any splitting caused by weak imperfections becoming exponentially small as the system grows. To transform one topological sector into another, you cannot simply flip a few nearby qubits and finish. A local flip creates pairs of excitations at the ends of a string. You may move one excitation step by step, extending that string through the lattice. If the excitation eventually travels all the way around the torus and reunites with its partner, the local disturbances disappear, yet a non-contractible loop has been written across the entire system. Only then has the global sector changed. The operation succeeds because it spans the topology of the whole surface. No bounded local process can reproduce it instantly. In the ideal toric code Hamiltonian, ordinary local evolution preserves these sectors. So 2 states can occupy the same physical lattice, share the same energy, and remain dynamically disconnected unless a system-wide loop operation is performed. This is not the same phenomenon as Hilbert space fragmentation, where kinetic constraints divide a large state space into many inaccessible regions. Here, the separation is topological. The states differ by a global property that cannot be detected or modified inside any small neighborhood. More generally, topological quantum order is characterized by ground states that look identical to every quasi-local measurement, while remaining distinguishable through non-local observables that wrap around the system. This protection is one reason topological states are attractive for quantum memory. Local noise does not immediately learn which logical state is stored, and one isolated error cannot directly change the encoded sector. But forever belongs to the idealized dynamics, not to every physical device. In a finite laboratory system, repeated local errors can accidentally join into a long string. Thermal excitations can move across the lattice, and environmental noise can eventually produce a loop large enough to corrupt the stored information. Weak perturbations may also cause an extremely small coupling between sectors rather than perfect separation. Active error correction, low temperatures, and increasing system size are therefore needed if the protection is to become practically long-lived. Yet the ideal principle remains profound. 2 states do not have to be separated by distance, energy, or an ordinary physical wall. They can occupy the same atoms and remain locally indistinguishable while belonging to different global histories of connection. You may search every small region and find no border between them, because the border is not anywhere in particular. It lies in the way the entire system wraps around itself. The 2 states share the same world, but the permitted local dynamics cannot carry one into the other, as though they were 2 stories written on the same page whose difference becomes visible only when you follow a line all the way around the universe and return to where you began. A quantum system can become trapped by rules that are not ordinary energy barriers. Give a quantum excitation all the energy it could possibly need to move, and it may still remain fixed in place because motion itself would violate one of the system's deeper rules. This is the strange idea behind fracton-like quantum matter, where certain excitations are trapped not by walls, disorder, or an energetic hill they cannot climb, but by conservation laws that restrict which rearrangements are physically allowed. Ordinary particles conserve quantities such as electric charge. A charged particle can move from one site to another without changing the total charge of the system. Some theoretical models conserve both charge and dipole moment, a quantity that depends on how charge is distributed through space. If one isolated charge moves to the right, the system's dipole moment changes, so the move is forbidden unless another charge moves in a compensating way. The particle may possess plenty of energy, and the destination may be completely empty, yet no legal local step connects its current position to that destination. It behaves as an immobile fracton. A pair of opposite fracton charges can be more mobile, because moving the pair together preserves their total dipole moment, creating the unusual situation in which a composite object moves more freely than either of its individual parts. Fracton theories generalize familiar gauge principles and show how higher conservation laws can produce excitations restricted to a line, confined to a plane, or unable to move at all. Similar restrictions have been studied in more realistic condensed matter models. In a hole-doped honeycomb lattice icing magnet, for example, an emergent subsystem symmetry can prevent an isolated hole from moving while permitting paired holes to travel along one direction, demonstrating how a microscopic pattern of spins can create nearly exact mobility rules without surrounding the particle with an ordinary potential barrier. The excitation is not frozen because time has stopped. It can interact, influence nearby degrees of freedom, join with another excitation, or become mobile when the conservation rule is satisfied. Nor is the restriction guaranteed to survive every perturbation. Additional interactions that break dipole conservation can create slow escape routes, and many proposed Fracton phases remain theoretical rather than established materials found in nature. What the models demonstrate is a different kind of confinement. You usually imagine that an object fails to move because the route demands too much energy, like a stone trapped at the bottom of a valley. Here, the landscape may be perfectly flat. The problem is that the rules do not contain an allowed move corresponding to one lonely step. The excitation is like a chess piece placed on an empty board with unlimited strength, but no legal direction in which it is permitted to travel. Only by joining another piece, altering the surrounding pattern, or breaking the symmetry can it escape. This changes the meaning of being trapped. A quantum system may explore many internal possibilities while remaining unable to perform the simplest translation through space, not because nature resists the motion with force, but because the motion would rewrite a quantity the universe has been instructed to preserve. Beneath ordinary matter, freedom may therefore depend on more than available energy. It may depend on whether the desired future can be reached through any sequence of moves the laws are willing to recognize. A system can hide a phase transition inside a few rare excited states. Almost every excited state in a quantum system can behave as though nothing important is changing, while a tiny hidden family undergoes a phase transition of its own. Conventional quantum phase transitions are usually introduced through the ground state, the lowest energy condition available to a system. As an interaction or external field is adjusted, that ground state can reorganize sharply, changing its symmetry, correlations, or long-range order even at zero temperature. Highly excited states in a chaotic many-particle system are expected to behave very differently. They normally resemble thermal states, and neighboring states at similar energy tend to display nearly the same local properties. Quantum many-body scars are rare exceptions buried inside this thermal spectrum. They possess unusually low entanglement, preserve special structures, and can support non-thermal dynamics, even though the overwhelming majority of states around them behave chaotically. Recent theoretical work has shown that a phase transition can be embedded specifically inside such scar states, while most of the surrounding spectrum remains largely unaffected. The researchers began with a specially structured matrix product state whose internal correlations change at a critical value of a control parameter. They then constructed a larger, non-integrable Hamiltonian in which that state appears as an exact highly excited scar rather than as the ground state. As the parameter is varied, the scar changes phase, its correlation length, entanglement structure, and other diagnostic properties develop critical behavior, while ordinary excited states at nearly the same energy continue looking thermal and show no comparable transition. The phase transition is therefore not spread evenly across the energy spectrum. It is concentrated within a vanishingly small set of atypical states, like a secret change of climate taking place along one narrow path through a continent that otherwise experiences the same weather. Numerical results suggest that near the critical point, additional low-entropy states may appear close in energy to the scar, helping the rare state alter its structure without forcing the surrounding thermal sea to reorganize. This is distinct from an ordinary, excited state quantum phase transition, which is often associated with a critical energy affecting the density and properties of a broad collection of excited levels. A scar state transition belongs instead to exceptional eigenstates selected by their structure rather than simply by how much energy they contain. The idea is currently a theoretical proposal supported by model calculations, not an experimentally confirmed universal phase of real materials. Detecting it would require preparing or targeting the rare scarred state with high precision, because a generic initial condition would overlap mostly with ordinary thermal states and could pass through the same parameter change without displaying the hidden transition at all. Yet this selectivity is exactly what makes the possibility so profound. You are accustomed to thinking that a phase belongs to the entire system. Water is liquid, a magnet is ordered, a material is superconducting. Quantum mechanics allows a more private form of organization. The same Hamiltonian, the same particles, and nearly the same energy can host one rare state on one side of a critical boundary, while countless neighboring states remain oblivious to it. The transition is real within the scar's correlations, but invisible to anyone who examines only typical states. Nature may therefore conceal an entire change of order, not in a different material or a colder temperature, but inside a few exceptional arrangements, hidden among an ocean of states that have already forgotten how to be special. A microscopic machine can borrow order from coherence, send ordinary excited atoms through a tiny optical cavity, and they release energy mostly as unrelated flashes. Prepare those same atoms with a shared quantum phase, and the cavity can suddenly behave as though it has been connected to a far more powerful source. This is one of the clearest ways a microscopic machine can borrow order from coherence. Quantum coherence means that different possible states of an atom retain a precise phase relationship instead of becoming an ordinary statistical mixture. The populations of the atomic energy levels may remain nearly unchanged, so a simple energy measurement can make two atomic reservoirs look similar. Yet the coherent reservoir contains an additional form of organization. When many coherently prepared atoms pass through a cavity, their emission amplitudes can reinforce one another. Rather than acting like isolated lamps switching on at random, the atoms radiate collectively through a process called superradiance, creating a stronger and more ordered field than the same number of independently prepared atoms would produce. In a proof-of-principle photonic quantum engine experiment, researchers prepared reservoir atoms in coherent superpositions and sent them through an optical cavity one after another. The collective emission increased the cavity's effective temperature by roughly 40 times, produced near-unity reported engine efficiency under the experiment's resource accounting, and caused the output power to grow approximately with the square of the atomic injection rate, rather than only in direct proportion to it. The working substance did not manufacture energy from an empty phase relation. The atoms supplied real excitation energy, while their coherence controlled how efficiently and collectively that energy entered the cavity field. The machine was therefore borrowing two things at once: energy from the atomic populations and order from the phase relationship connecting the possible atomic states. That borrowed order made random microscopic emission behave more like coordinated motion, allowing the cavity field to build with less of the destructive cancellation expected from independent emitters. Theoretical studies of quantum heat machines likewise distinguish between stochastic power created by ordinary population transfers and coherent power produced when quantum amplitudes contribute in a phase-sensitive way. Under suitable operating conditions, the coherent contribution can push the output above bounds obeyed by comparable fully dephased machines. But coherence is not universally beneficial. In slowly driven engines or poorly designed cycles, it can increase internal friction, generate extra dissipation, and reduce power instead of enhancing it. The advantage depends on where the coherence is stored, how it interacts with the working medium, and whether the machine converts it into directed output before the environment destroys it. Nor does the experiment defeat the second law or obtain unlimited work from one ordinary heat bath. A coherent reservoir is not an ordinary thermal reservoir. Preparing each atom in the required superposition costs resources, and after interacting with the cavity, the atoms no longer carry the same useful coherence. To operate continuously, the supply of ordered atoms must be recreated, so the full thermodynamic balance includes the machinery that prepares them. The microscopic engine resembles a windmill placed in air whose molecules have briefly been encouraged to move in rhythm. The windmill benefits from that rhythm, but it did not create the rhythm and cannot preserve it forever. Each atom lends a small portion of organized possibility. The cavity combines those contributions into a stronger field, and the coherence gradually becomes ordinary energy and lost phase information. What the machine reveals is that order itself can perform a physical task. Energy tells you how much change may be possible, but coherence can determine whether countless tiny changes cancel into noise or gather into one usable motion. At microscopic scales, a machine may therefore be powered not only by how excited its fuel is, but by how carefully the possibilities inside that fuel still remember one another. Knowing something about a particle can change the thermodynamic cost of erasing it. Particle can become cheaper to erase simply because another physical memory already knows where it is. Imagine a 1-bit memory represented by a microscopic particle trapped in one of two wells. The left well means 0, the right well means 1, and erasing the bit means forcing the particle into the same chosen well, regardless of where it began. When both starting positions are equally possible, and you possess no information about which one is occupied, the operation compresses two distinguishable possibilities into one. Landauer's principle states that this loss of information carries a minimum thermodynamic cost proportional to the temperature of the environment. Experiments with single colloidal particles have confirmed that slowly erasing an unbiased bit approaches this Landauer limit on average. But now suppose a second memory records the particle's initial location. If the record says left, you can use a protocol designed specifically for the left well. If it says right, you use the mirrored protocol. Because you are no longer compressing an unknown pair of possibilities, the minimum work required for the particle's reset can be reduced. With perfect, reliable side information and ideal reversible control, the erasure cost of the target can approach 0. Partial knowledge gives an intermediate reduction. The more uncertainty the side information removes, the less thermodynamic entropy must be expelled while resetting the particle. In the quantum formulation, the relevant quantity is not simply the uncertainty of the particle by itself, but its uncertainty conditioned on the information stored in the observer's memory. Lidia Del Rio and colleagues showed that this conditional information determines the fundamental work cost of erasure when the side memory can itself be quantum mechanical. Strong quantum correlations can reduce the cost below the ordinary Landauer value, and in extreme theoretical cases, the erasure step can even release usable work while resetting the target. This does not mean that personal awareness cools a computer, or that merely guessing the particle's position changes physics. The knowledge must exist as a trustworthy physical correlation, a second bit, a quantum memory, a measurement record, or another system whose state is linked to the particle. It must also be accessible to the mechanism performing the erasure. A record locked in a distant box cannot reduce the local cost unless its information is communicated or physically incorporated into the protocol, and the saving is not free. If the assisting memory is to be reused, it may eventually need to be erased as well. Resetting that record restores the cost that seemed to disappear, preserving the complete thermodynamic balance. If the memory is allowed to accumulate records indefinitely, the cost has not vanished. It has been postponed and stored as growing informational disorder elsewhere. This is the resolution of Maxwell's demon. A demon may observe individual particles and use the results to extract work from their motion, but a cyclic demon must eventually clear its memory, and that reset closes the apparent loophole. The same principle applies even when the information is quantum. Correlations can shift the location and timing of the cost, but they cannot make the full physical accounting disappear. There is another subtlety. Knowing the state changes the optimal protocol, not necessarily the energy landscape of the particle itself. Two laboratories can hold physically identical particles at the same temperature while facing different minimum erasure costs, because one laboratory possesses a useful record and the other does not. Thermodynamic value therefore depends partly on relationships between systems, not only on the visible condition of the system being manipulated. You might think that erasure means destroying something stored inside the particle, but the true cost concerns how many possibilities remain unresolved from the perspective of the available physical information. When another memory has already narrowed those possibilities, less uncertainty must be pushed into the environment. The particle has not become colder or lighter. The world around it has become more informed, and that information quietly changes how much work nature demands before the past can be reset to one chosen state. Timekeeping itself may consume a physical quantum resource. A quantum clock cannot reveal the passage of time unless something inside it possesses the physical ability to change distinguishably from one moment to the next. Place a quantum system in one definite energy state, and apart from an overall phase that no measurement can detect, it does not provide a moving hand. Even an ordinary mixture of different energies lacks a reliable internal rhythm because no definite phase relationship connects its components. A useful quantum clock instead prepares a coherent combination of energy levels. As time passes, the relative phases between those levels evolve, causing the state to move through a sequence of distinguishable configurations that can be compared with another system. In the language of quantum resource theory, this ability is called asymmetry with respect to time translation. The clock is useful precisely because its state does not look identical after every shift in time. Energetic coherence is therefore not decorative uncertainty added to the clock. It is part of what allows the device to mark when an event occurred and how much time has elapsed. Research connecting quantum speed limits with asymmetry has shown that a state's capacity to evolve into distinguishable configurations is directly related to this resource, while later work has identified energetic coherence as indispensable for precise time measurements and other operations requiring a temporal reference. Yet a finite clock cannot offer an infinitely sharp temporal reference without consequences. When another system is measured relative to it, the interaction can disturb the clock, transfer part of its timing information into correlations, or gradually reduce its usefulness as a shared phase reference. Studies of finite quantum reference frames show that repeated measurements can degrade their performance through unavoidable backaction, meaning that a microscopic clock may have only a limited number of accurate uses before it must be restored or replaced. There is also a second cost hidden behind the visible tick. An autonomous clock must operate without an external experimenter secretly turning its controls at prearranged times, because such control would already assume access to another clock. To produce a directed stream of ticks on its own, the device must be maintained away from equilibrium. A model powered by hot and cold reservoirs found a trade-off between the heat dissipated by the clock and the accuracy and resolution of its ticks. Greater reliability required greater entropy production. Experiments with a nanoscale membrane later measured a near-linear relationship between entropy generated per tick and clock accuracy, while a quantum dot clock experiment separated the cost of producing microscopic tunneling events from the much larger cost of detecting, amplifying, and recording them. The latter study found that the readout apparatus could dissipate far more power than the clockwork itself, even though that measurement record greatly improved the estimate of time. None of this means that an ideal isolated superposition loses coherence merely because it evolves. Under perfectly controlled unitary motion, the phase relationship can rotate without being consumed. The cost appears when the clock must be prepared, stabilized against noise, compared with other systems, converted into readable ticks, and reset for continued use. A classical wall clock hides similar expenses in its battery, friction, electronics, and discarded heat. But quantum theory makes the informational ingredient impossible to ignore. To tell time, a physical object must break the symmetry between one moment and another, and to communicate that distinction, it must leave a record somewhere. The clock does not stand outside the universe watching time pass for free. It participates in the passage it measures, lending coherence to define the moment and producing entropy so that the moment will not be mistaken for the one before it. Nature may complete a task without using any definite sequence of events. Two unknown quantum operations can each be used only once, yet a device can determine whether they cooperate or oppose one another without ever assigning them one definite overall order. Imagine receiving two sealed quantum gates whose internal actions are unknown. You are promised only that they belong to one of two categories. In the first, performing gate A and then gate B has the same effect as performing B and then A. The gates commute. In the second, reversing their order introduces a minus sign. The gates anti-commute. That minus sign creates a peculiar obstacle. If you choose a standard circuit and send a particle through A followed by B, you observe only the final state produced by that sequence. The alternative sequence would produce either the same state or the same state multiplied by a global negative phase. A global phase cannot be detected by itself, so one fixed sequence using each gate once cannot reveal which promise was true. A quantum switch changes the question. A control qubit is prepared in a superposition of two routes. Along one route, the target encounters A and then B. Along the other, it encounters B and then A. The routes are recombined coherently, so the two possible orders are not merely chosen by an unseen coin and forgotten. If the gates commute, both branches return with the same phase and reinforce one control outcome. If they anti-commute, one branch carries the opposite phase, turning the formerly invisible global sign into a measurable relative phase between the routes. Reading the control qubit then identifies the relationship between the gates, while each operation has been queried only once. A photonic experiment implemented this two-operation quantum switch and demonstrated the commuting versus anti-commuting test with a single use of each unknown gate, whereas a fixed-order circuit requires at least one of the gates to be used again. The machine has not discovered which gate really happened first behind the experiment. Its success depends on preserving coherence between the two orderings until the final measurement. So replacing the control with an ordinary random switch would destroy the relative phase carrying the answer. This is also more specific than merely running two normal circuits in parallel and comparing them, because that strategy would require additional calls to the unknown operations. The task is solved by allowing the ordering itself to become a controlled quantum degree of freedom. There are important experimental and conceptual qualifications. Every component still operates through ordinary local interactions. The photon does not travel backward in time, and no result can be used for communication into the past. Researchers have also examined whether some laboratory implementations simulate the switch by allowing the physical devices to be encountered more than once. Models that explicitly count energetic restrictions still find regimes in which a genuine quantum switch performs the same discrimination task better than such fixed-order simulations, though the precise resource accounting depends on how a use of a physical operation is defined. Nor does indefinite order automatically accelerate every computation. The advantage appears in tasks whose answer is encoded in the relationship between operations and can be exposed by interference between their possible sequences. Here, the remarkable step is simple. A sign that would remain physically meaningless inside either definite order becomes observable when two orders coexist coherently. Nature completes the task without selecting one timeline for the operations, not because causality has vanished, but because the process contains information that no individual sequence can hold. You begin by asking whether A should come before B or B before A. The quantum device answers that for this task, the useful physical question was never which order occurred, It was how the two possible orders were allowed to interfere.